What if everything you know about reality is an illusion? Take a moment to look around. Your surroundings, the objects near you, even your own hands, they feel real, solid, undeniable. But what if you were told that modern science, ancient philosophy, and cutting-edge technology all point to a shocking possibility? Reality may not be what we think it is. From quantum physics suggesting that particles exist in multiple states at once, to philosophers questioning whether we even have free will, the very fabric of existence seems to unravel the closer we examine it. Could we be living in a vast simulation? Is reality just an elaborate construct of our minds? Or is there an ultimate truth hidden just beyond our perception? Join us as we dive deep into the mind-bending question about what reality is. To our most ancient ancestors, reality was clear and straightforward. Whether they lived on the vast grasslands of Africa or roamed the icy landscapes of what we now call Northern Europe, their world was defined by what they could see, hear, touch, taste, and smell. Reality was not an abstract idea, it was the immediate and urgent world around them. A snapping twig in the forest could mean two very different things. It might signal that food was nearby, perhaps a deer or a wild boar, but it could also mean danger, a lurking predator with sharp teeth and deadly claws. For them, understanding reality was not a matter of philosophy, it was a matter of survival. Because of this constant struggle to stay alive, these early humans may not have had much time to ponder the deeper nature of existence. Their minds were occupied with finding food, shelter, and staying safe. But as human brains grew more complex and our thoughts expanded, the way we understood reality began to change. We know that humans began to bury their dead nearly 100,000 years ago. What went through their minds as they laid their loved ones to rest? Did they grieve as we do? Did they believe in an afterlife? While we may never know their exact thoughts, these early burials suggest that humans were beginning to think beyond the physical world. They were imagining something beyond what they could see and touch, perhaps a spirit world, an afterlife, or unseen forces that shaped their lives. Over time, ideas of gods, spirits, and mysterious forces took shape. People started to seek meaning beyond their daily struggles. They wondered why the world existed, what their purpose was, and whether invisible forces guided their fate. But not everything requires deep thought. Take the simple apple, for example, a fruit given to us by the gods, some believed. There was no need to question its reality. You could hold it, bite into it, taste its sweetness. It was real. But was everything as simple as the apple? Or was there more to reality than what meets the eye? One of the first great thinkers to explore this question was Plato, a philosopher from ancient Greece who lived in the city of Athens more than 2,300 years ago. His real name was Aristocles, but he was known as Plato, a nickname meaning broad, likely because of his strong build. Plato was troubled by the physical world. He wondered why things had the properties they did. Why is the sky blue? Why do dogs have 4 legs? What makes an apple red? He believed that the world we see around us is not the true reality, but only a shadow of something deeper and more perfect. To explain this, Plato told a famous story, the allegory of the cave. Imagine a group of prisoners who have been chained inside a dark cave their entire lives. They cannot move or turn their heads. All they can see is the wall in front of them. Behind them, outside the cave, is the real world, full of people, animals, and sunlight. But the prisoners do not see any of this. Instead, the only thing they see are shadows on the cave wall. These shadows are cast by figures passing by the cave entrance, with sunlight creating their outlines. For the prisoners, these flickering shadows are their entire reality. They do not know about the real people outside the cave. They only know the moving shapes on the wall. But what if someone blocked the cave entrance and lit a fire inside? Now, instead of real shadows from the outside world, tricksters could use the firelight to create puppet shows on the wall. These shadow puppets could tell stories of monsters, warriors, castles, and kings. The prisoners, having never known anything else, would believe these stories to be real. To them, this new world of shadows would be no less true than the one before. Plato used this story to suggest that we too might be like the prisoners in the cave. What if the reality we experience every day is just a projection, a mere shadow of something far greater? What if everything we know is just an imperfect reflection of a deeper, more perfect truth? Incredibly, modern science has found some eerie similarities to Plato's ideas. As we have explored the nature of matter, time, and space, we have discovered that reality is far stranger than we ever imagined. Ancient philosophy, as insightful as it was, could not reveal the full picture. To truly understand reality, we had to turn to science, and the deeper we looked, the weirder things became. In the early months of the year 1821, the young poet John Keats took his final breath in the city of Rome. He was only 25 years old, but his body had been ravaged by tuberculosis, a disease that showed no mercy. Despite his short life, Keats left behind a remarkable legacy. He had a deep appreciation for the beauty of nature and captured it in his poetry, weaving words into vivid images that stirred the soul. Yet, like so many great artists before and after him, his true genius was only fully recognized after his death. Keats was born nearly 70 years after the passing of the great scientist Isaac Newton. He lived during the era of the Industrial Revolution, a time when the world was rapidly changing, powered by scientific breakthroughs, many of which could be traced back to Newton's discoveries. Newton and other scientists of his time had begun peeling away the mysteries of existence, revealing that much of what seemed magical was actually governed by precise and predictable physical laws. One of Newton's most famous discoveries was about light. He realized that the bright white light of the sun was not a single color, but a mixture of all the colors of the rainbow. He proved this by passing sunlight through a prism which separated it into a beautiful spectrum, from deep red to rich violet. Before this discovery, the rainbow was seen as a mystical wonder, a breathtaking phenomenon painted across the sky by nature itself. But Newton, with his relentless pursuit of knowledge, stripped away its mystery and explained it in terms of physics. Keats, however, did not see this as a triumph. To him, Newton had drained the beauty and magic from the world by reducing the rainbow to mere science. He famously lamented that Newton had unwoven the rainbow, taking something that once inspired awe and turning it into nothing more than a mechanical process. But what Keats saw as a loss, Newton saw as progress, the beginning of a scientific revolution that would forever change our understanding of reality. And so, Newton's work laid the foundation for a long tradition of scientists who sought to uncover the hidden structure of the universe. This quest led to more questions about light, about perception, and even about the very nature of reality itself. Now, let's consider something as simple as an apple. We recognize a ripe apple by its vibrant color. But what does that color actually mean? Apples are made up of water, sugars, and complex organic structures, yet our eyes see them as red or green. Why? To answer this, we must explore the meaning of color itself. And our journey begins with a man who was once called the last person to truly know everything: Thomas Young. Young was born in the small town of Milverton, Somerset, in the year 1773. A child prodigy, he had an insatiable thirst for knowledge and learned an astonishing number of languages, including French, Greek, Latin, Italian, Aramaic, and Persian. He played a crucial role in deciphering Egyptian hieroglyphics after the Rosetta Stone was discovered. However, Young is best known for something else, an experiment that forever changed the way we understand light. His experiment, known as the double-slit experiment, would reveal that light was far more mysterious than anyone had imagined. But before we delve into that, let's return to the subject of color. Artists have long known that mixing different paints can create new colors. But Young took this idea further. He proposed that the human eye contains 3 different types of color receptors, what we now call cone cells. Each type responds to a different color: red, green, or blue. Our brain takes the signals from these 3 receptors and blends them, allowing us to perceive a full range of colors. But here's where things get even stranger. Not all creatures see the world the way we do. Our closest relatives, monkeys and apes, have similar vision to ours, detecting 3 primary colors. But most other mammals, such as dogs and cats, only see 2. Their world is missing the richness of the red spectrum. Then there are creatures with even more advanced vision. Bees, for example, can see ultraviolet light, which is completely invisible to us. Birds, reptiles, and fish often have 4 or more types of color receptors, giving them an expanded view of the world. But the champion of color vision is the mantis shrimp. This tiny but ferocious sea creature possesses an astonishing 12 different types of color receptors. It sees colors we can't even begin to imagine. What does this mean for us? It tells us something profound. Color is not an inherent property of objects. It is a perception, a construct created by our brains. The bright yellow of a banana exists only in our minds. To another creature, the same banana might look blue, purple, or even the same color as human skin. And if color is merely an illusion, what about everything else we experience? The sounds we hear are nothing more than vibrations in the air, transformed by our ears into electrical signals that our brains interpret as music, speech, or noise. In many ways, we live inside a reality of our own making, a world shaped by the limitations of our senses. Newton gave us the explanation for rainbows, but the colors we see exist only within us. The question is, if our perception of reality is not truly reality, then what is? For centuries, we thought we could at least trust space and time. An apple exists here and now. That seems like an undeniable fact. But as science progressed beyond Newton and Young, even these fundamental truths were called into question. In the distant past, time flowed at a slower pace than it does today. Scientists in the year 2023 set out to measure exactly how much slower it was. To do this, they turned their attention to some of the most powerful and ancient objects in the universe: quasars. These quasars, located nearly 12 billion years in the past, are gigantic black holes that contain masses billions of times greater than our Sun. The immense gravity surrounding these cosmic giants pulls in matter at astonishing speeds, nearly reaching the speed of light. As this matter spirals inward, it becomes incredibly hot, reaching temperatures of billions of degrees, emitting a glow so bright that it can be seen across the universe. However, before this matter is consumed by the black hole, it undergoes a violent process, smashing into itself and releasing bursts of light in an almost rhythmic fashion, much like a cosmic fireworks show. Astronomers studying this flickering glow noticed something remarkable: a hidden pattern. They realized that this flickering light could act as a kind of cosmic clock, allowing them to measure the passage of time in the early universe. By comparing the ticks of these ancient quasar clocks to modern timekeeping, astronomers made a fascinating discovery. The farther away a quasar was, the slower its time appeared to move. When the universe was only 1/10 of its current age, time was flowing at just 1/5 the speed it does today. This discovery was breathtaking, but it wasn't unexpected. The concept of time slowing down across vast cosmic distances was already predicted by a theory written over 100 years earlier, a theory that forever changed how we perceive space and time. The origins of this groundbreaking understanding of space and time can be traced back to a cold night in the early 17th century. In the year 1619, a French philosopher and mathematician named René Descartes found himself shut away in a small room, seeking warmth from the bitter cold. At the time, Descartes was serving as a soldier for the Dutch Protestant state, But his mind was more occupied with deep intellectual pursuits than with warfare. As the story goes, Descartes lay in bed, staring absent-mindedly at the ceiling when he noticed a small fly moving across the room. The fly wandered along the ceiling, then darted to the wall, then moved back again. As Descartes watched its erratic movements, a thought struck him. How could he precisely describe the fly's journey? He realized that to track the fly's motion, he needed a fixed reference point. This reference point could be anywhere, but it had to remain consistent. He also saw that simply measuring the distance between the fly and this reference point wasn't enough. He needed to account for direction too. Then, in a moment of insight, Descartes saw a way to simplify the problem. He chose the corner of the room where the walls met the ceiling as his reference point. From there, he imagined 3 imaginary lines, one along each edge of the room, forming 3 perpendicular axes. By measuring the fly's position along these 3 axes, he could describe its exact location at any given moment using just 3 numbers. This simple but powerful idea became the foundation of what we now call the Cartesian coordinate system, a mathematical system that allows us to describe any point in 3-dimensional space using just 3 coordinates. Today, this system is so fundamental that even young students learn about it in elementary school. Scientists, engineers, and mathematicians rely on it daily to solve complex problems. Though Descartes passed away in the year 1650, his ideas laid the groundwork for a new way of understanding motion and space, one that would soon be expanded upon by another great thinker. At the time of Descartes' death, a young boy named Isaac Newton was growing up in the English countryside. Newton would go on to take Descartes' ideas even further, developing the mathematical framework that would define classical mechanics. In Newton's universe, time was seen as absolute, a single clock ticking uniformly across the cosmos, a measurement that all observers would agree on. Space, however, was slightly more complex. Around the same time as Descartes, another great thinker, Galileo Galilei, had been pondering the nature of motion. Galileo approached the problem not with complex equations, but through simple thought experiments. He imagined being on a ship, wondering whether there was any way to tell if the vessel was moving if you were sealed inside without looking outside. He realized that if the ship was either at rest or moving smoothly across calm waters, everything inside would behave the same way. Objects would fall straight down, and people would walk normally. However, if the ship accelerated, slowed down, or rocked on rough waves, the movement of objects would change. Plates would slide off tables, and people would struggle to keep their balance. From this, Galileo concluded that there is no absolute state of rest in the universe. Motion is always relative. The laws of physics remain the same for any observer moving at a constant speed. This idea became the foundation of what we now call the first theory of relativity. Newton later incorporated Galileo's insights into his own work, creating the 3 laws of motion. These laws allowed anyone, anywhere, to predict how objects would move under different conditions. If you were to drop a ball while standing on a stationary train platform, the ball would fall straight down to your feet. But if you performed the same experiment on a train moving at a constant speed, the ball would still appear to fall straight down relative to you. However, if the train was speeding up or slowing down, the ball's motion would seem strange. It might veer toward the back or front of the train, not because of any actual force acting on it, but because your frame of reference was accelerating. For centuries, Newton's framework was seen as the ultimate description of reality. His ideas formed the backbone of physics, and for a long time, they seemed unshakable. However, as the 19th century approached, scientists began uncovering new mysteries about light, mysteries that Newton's laws could not explain. One Scottish physicist, James Clerk Maxwell, finally revealed the truth about light's nature, leading to discoveries that would completely revolutionize our understanding of space, time, and the fabric of the universe itself. James Clerk Maxwell changed the world of science in a way few had before him. By the middle of the 1800s, he had done something remarkable. He found a way to connect electricity and magnetism using mathematics. Before him, scientists had noticed strange hints that these two forces were linked, but no one had been able to prove it. Maxwell, however, put everything together in just a few equations, showing that electricity and magnetism were not separate forces, but actually two parts of the same phenomenon. This discovery alone made him famous in the scientific world. But Maxwell didn't stop there. When he looked deeper into his equations, he uncovered something even more astonishing. He realized that light itself was an electromagnetic wave, a ripple in the combined fields of electricity and magnetism. His equations also revealed something mind-blowing: the speed of light. He calculated that it moved at an astonishing 300,000 kilometers per second. However, there was a mystery. This speed was fixed, but what was it relative to? In other words, what background or reference point determined this speed? Many scientists at the time believed that there must be an invisible substance called the ether, filling the universe, acting as the medium through which light traveled. They designed experiments to detect this ether. Some involved bouncing light off mirrors, while others used electric currents to light bulbs, all in an attempt to see if light behaved differently depending on how the observer moved relative to this invisible substance. If the ether existed, it would mean that the universe had a fixed state of rest, a universal reference frame. But there was a problem. This idea went against Galileo's principle of relativity, which stated that the laws of physics should work the same way for all observers, no matter how they were moving. If electromagnetism required an absolute reference frame, why didn't other areas of physics? Why would this one force behave differently from everything else? It made no sense. Then, in the year 1905, a young physicist named Albert Einstein stepped in with a bold idea. He argued that the universe was not divided into two kinds of physics, one that followed Galileo's laws and one that did not. Instead, electromagnetism had to obey the same rules as everything else. And with that realization, the special theory of relativity was born at the dawn of the 20th century. At the heart of Einstein's theory was a simple yet radical idea. All observers, no matter how they were moving, must agree on the results of experiments involving electromagnetism. But this came with an unexpected consequence. Every observer had to measure the same speed of light. No matter how fast you were moving, no matter what reference frame you were in, light always moved at 300,000 kilometers per second. This idea was impossible to explain using Isaac Newton's understanding of space and time, which treated them as fixed and absolute. Einstein realized that for his theory to make sense, space and time had to be flexible. That meant that distances and even the passage of time could change depending on who was measuring them and how fast they were moving. This sounded crazy. In our daily lives, time and space feel constant. An hour is always an hour, and a meter is always a meter. But when objects move at speeds close to that of light, everything changes. And in the 1960s, scientists found undeniable proof that time could actually slow down under the right conditions. They focused on tiny particles called muons, which are similar to electrons but much heavier. Unlike electrons, which last forever, muons exist for only about 2/millionths of a second before they break apart into other particles. Scientists knew that high-energy muons were created in the upper atmosphere when cosmic rays from space collided with gas molecules. Based on their short lifespan, the muons should have traveled only about half a kilometer before decaying. But when scientists measured them, they found something shocking. Muons were reaching the ground after traveling tens of kilometers. How was this possible? The answer lay in Einstein's theory. The key to understanding this was something called the Lorentz factor, which describes how time stretches when objects move close to the speed of light. From the muon's point of view, its lifetime was still just 2/millionths of a second. But from the perspective of scientists on Earth, the muon's clock was ticking much slower, allowing it to live longer and travel much farther than it should have. This was proof that time could be stretched when speeds approached that of light. But time wasn't the only thing that could change. Space could as well. If you could ask a muon about its journey, it would say it had only traveled a few hundred meters before decaying. To the muon, the distance to the ground had shrunk. This showed that both space and time could be warped when moving at high speeds. Einstein also realized that the speed of light wasn't just a limit for objects. It was also a limit for how fast information could travel. Nothing, not even a signal or a message, could go faster than light. This meant that we never see the universe as it is at this exact moment. Instead, we see everything as it was in the past. For example, when we look at the sun, we are actually seeing it as it was 8 minutes ago, the time it takes for light to travel from the sun to Earth. When we look at the Andromeda Galaxy, the nearest major galaxy to our own, we are seeing light that left there more than 2 million years ago, long before modern humans even existed. And when astronomers study distant galaxies through their telescopes, they are looking billions of years into the past. In a way, the universe as it truly is right now is hidden from us. All we can see is a snapshot of the past, frozen in the light that has finally reached us. But the consequences of relativity didn't stop there. Einstein realized that if time and space could be stretched and warped, then different observers could actually disagree about what was happening at the same time. Newton had imagined that time was universal, that there was one single now that applied everywhere. But Einstein showed that this was an illusion. Two events that appear to happen simultaneously to one observer might occur at different times for someone else. In other words, the idea of absolute synchronicity, the belief that events happen at the same time for everyone, was not real. This was a radical and unsettling idea. It meant that time itself was not fixed, but something flexible and relative. And yet, despite how strange it seemed, Einstein's theory of relativity has been confirmed time and time again through experiments. Today, we rely on it for everything from GPS satellites to understanding the behavior of black holes. Maxwell's equations started a chain reaction of discoveries that forever changed our understanding of reality. What began as a search to understand electricity and magnetism ended with a new vision of the universe. One where space and time could stretch, where time itself was not absolute, and where nothing could move faster than the speed of light. This was the beginning of modern physics, and it all started with a handful of equations written in the 1800s. Let's dive into one of Albert Einstein's famous thought experiments. Imagine a high-speed train rushing down the tracks. Inside, 3 people are positioned in different spots, one at the back, one at the front, and one right in the middle of the carriage. They decide to carry out a simple but fascinating experiment. The person standing in the middle has a special device that releases a flash of light. This light travels outward in both directions, toward the front and the back of the train. At each end, the other 2 people have mirrors that will reflect the light back toward the center. The moment the light reaches the mirrors and bounces back, the 2 people at the ends raise their hands. Now, in real life, this experiment would be over in an instant, and human reaction times might not be fast enough to match the speed of light. But that's the beauty of thought experiments. We can ignore these limitations and focus purely on the physics at play. From the perspective of someone inside the train, everything appears perfectly balanced. The light moves outward at the same speed in both directions, reflects off the mirrors, and returns to the center at the same time. It seems completely reasonable to say that both people at the ends raised their hands at the exact same moment. Everything was synchronized. But what happens if we change our perspective? Now, let's imagine an observer standing on the train platform watching this high-speed train zoom past. Except, for fun, let's say this train is moving incredibly fast, close to the speed of light. From this outsider's point of view, something very strange happens. According to Einstein's special theory of relativity, light always travels at the same speed for all observers, no matter how fast they are moving. This means that for the person watching from the platform, the situation unfolds differently. Since the train is moving forward at high speed, the back of the carriage is moving toward the incoming light, reducing the distance the light has to travel. Meanwhile, the front of the carriage is moving away, increasing the distance the light must cover before hitting the mirror. So, even though both beams of light were emitted at the same moment from the middle of the train, they don't reach their respective mirrors at the same time. The person standing on the platform sees the light reach the back mirror first and the front mirror later. This also means that the two people at the ends of the train don't raise their hands simultaneously from the platform observer's point of view. Inside the train, the event appeared perfectly synchronized, but for the observer outside, the sequence was staggered. This is where things start to get really weird. Time itself appears to behave differently depending on the observer. What is simultaneous for one person is not necessarily simultaneous for another. Synchronicity, it turns out, depends entirely on your point of view. Einstein was thrilled with his special theory of relativity, but he quickly realized a problem: gravity. Back in the 17th century, Isaac Newton had given the world his famous equations of gravity, explaining everything from the way apples fall from trees to how the moon orbits Earth. But Newton's laws relied on the idea of absolute time, where events happen at a specific, well-defined moment, what he called now. Einstein's theory, however, shattered the idea of a universal now. If time was relative, then how could you measure the exact distance between two objects in space when now isn't the same for everyone? This contradiction meant that Newton's version of gravity simply didn't fit within Einstein's new understanding of the universe. Instead of trying to force Newton's ideas into his equations, Einstein made a radical choice. He threw out Newton's concept of gravity altogether. He had to completely rethink what gravity actually was. The answer he found was even stranger than anything before. He discovered that space and time weren't rigid, fixed things. They were flexible, like a cosmic fabric that could bend and stretch. What we call gravity wasn't an invisible force pulling objects together, as Newton had thought. Instead, it was the bending of space and time itself. It took Einstein 10 years of intense work to fully develop this new theory, but by the year 1915, he had solved the puzzle. This groundbreaking idea became known as the general theory of relativity. Today, it is the foundation of our understanding of gravity. We now know that planets, stars, and even black holes warp the space-time around them, creating the effects we recognize as gravity. Einstein's equations don't just describe the movement of planets, they explain the expansion of the universe itself. They even power the technology we use every day, like the global positioning system, which must account for time running differently on satellites due to relativity. One of the most mind-bending ideas that comes from Einstein's work is that there is no universal clock ticking in the background of the universe. There is no single, agreed-upon now. Time and space can be stretched, distorted, and twisted depending on where you are and how fast you're moving. And this brings us to an incredible study from the year 2023. Scientists examining distant quasars, extremely bright objects powered by supermassive black holes, found evidence that, in the early universe, time appeared to run more slowly. But here's the catch. If you had been there billions of years ago, time wouldn't have felt slower to you. A single second would have still felt like a single second. However, as the universe expands, space-time itself stretches. This stretching affects the light traveling across the cosmos, making events from the distant past appear to unfold in slow motion when viewed from today's perspective. An even more extreme version of this effect happens near black holes. According to general relativity, time slows down dramatically in the presence of an immense gravitational pull. If you were to hover near the edge of a black hole while your friend watched from a safe distance, they would see you moving in slow motion. In fact, from their point of view, you might never appear to fall in at all. Einstein's ideas may sound like science fiction, but they have been tested over and over again, proving to be one of the most profound and accurate descriptions of our universe. Time is not absolute. Space is not rigid. And what now means depends entirely on who is observing. At the very heart of a black hole, space and time are twisted and stretched to unimaginable extremes. But even as you move closer to the edge of this cosmic abyss, known as the event horizon, space itself bends, and time starts acting strangely. If you were falling toward a black hole, your experience of time would slow down dramatically compared to someone watching from far away. This bizarre effect, called time dilation, happens both near black holes and across vast stretches of the universe's history. Even though these situations seem completely different, they follow the same fundamental rule. Time does not flow the same way for everyone, everywhere. At the beginning of the 20th century, a revolutionary idea reshaped our understanding of time forever. Albert Einstein's theories showed that time is deeply personal. It doesn't tick the same way for everyone. Imagine you have a watch on your wrist, or simply listen to the steady beat of your heart. To you, each second feels perfectly normal. But for someone moving at a different speed, standing in a stronger gravitational field, or even existing in another era of the universe, time could pass at a completely different rate. This bending and warping of time isn't just a strange theory, it's part of the real world. Scientists have observed it in action. Tiny particles called muons, created high in Earth's atmosphere, should decay long before they reach the ground, yet they survive because they experience time differently as they hurtle toward the planet. Scientists have also taken atomic clocks, some of the most precise timekeeping devices ever made, on airplane journeys around the world. When the clocks return, they no longer match the ones that stayed on the ground. Time for them has ticked at a slightly different speed. And here's where things get even wilder. We could, in theory, use this strange nature of time to travel into the future. If you spent time near a black hole, where gravity is so intense that time slows almost to a stop, you could return to find that years or even centuries had passed for the rest of the universe, while only minutes or hours had passed for you. In a way, black holes could serve as natural time machines, pulling people forward in time without them even realizing it. But what does this all mean for the way we experience reality? Right now, you might be looking at an apple sitting a short distance away, feeling certain that it exists in the same moment as you. But Einstein's discoveries force us to rethink this certainty. Your now is uniquely yours. Your present moment belongs only to you. Someone moving differently or existing in a different place might experience a completely different now. In the month of May, in the year 1932, the front page of the Melbourne Argus screamed with excitement. It was a headline that captured the world's attention, even though it was printed nearly 20,000 kilometers away from the laboratory in Cambridge, where the breakthrough had taken place. The discovery was so astonishing that it shook the very foundation of what scientists understood about reality. For thousands of years, philosophers and thinkers had dreamed of unlocking the deepest secrets of matter. That dream was finally realized by two British scientists, Ernest Walton and John Cockcroft. These men were like modern-day alchemists, but instead of using fire and potions, they worked with gleaming metal instruments, electric currents, and powerful magnetic fields. Their tools were not cauldrons, but high-voltage devices that could accelerate tiny particles to unimaginable speeds. And with this cutting-edge technology, they did the impossible. They split an atom. Their target was lithium, a simple metal. But under the intense force of their experiment, it shattered, transforming into something new: 2 helium atoms. This was not just an ordinary scientific achievement. It was proof that atoms, long believed to be the fundamental, unbreakable building blocks of nature, could indeed be broken. The ancient puzzle of matter. For centuries, philosophers had debated the true nature of the physical world. Why do different materials behave so differently? Stones are hard, unyielding, and firm, while human flesh is soft and flexible. Were they made of entirely different substances? Or was there something deeper that connected them? Ancient Greek and Indian thinkers were among the first to propose an extraordinary idea that all things were made up of unimaginably small, indivisible pieces, which they called atoms. The name itself came from the Greek word meaning uncuttable. These tiny building blocks, they believed, formed everything in existence. But for thousands of years, this remained just a theory, a philosophical concept without any solid proof. Then, in the 18th century, scientific experiments began to hint that atoms were real. But surprisingly, it wasn't physicists who first uncovered the evidence. It was a botanist. The mystery of dancing pollen. The scientist was Robert Brown, born in Scotland in the year 1773. Over the course of his career, Brown traveled the world, studying plant life aboard a ship called the Investigator. But it was much later, in the year 1827, that he made a discovery that would change everything. While observing tiny pollen grains floating on water under a microscope, Brown noticed something peculiar. The grains didn't stay still. They moved in a constant jittery dance, bouncing in unpredictable directions. At first, he thought they might be alive, propelling themselves somehow. But when he tested the same experiment with non-living substances like fine chalk dust, he saw the same effect. This strange movement, which became known as Brownian motion, remained a mystery for nearly 80 years. Then, in the year 1905, a year now remembered as one of the greatest in scientific history, Albert Einstein provided the answer. Einstein's brilliant insight. That year, known as Einstein's Annus Mirabilis, Latin for miracle year, saw him revolutionize physics with multiple groundbreaking discoveries. While his theory of special relativity, which reshaped our understanding of space and time, is the most famous, he also made a breakthrough in quantum physics with his work on the photoelectric effect. But in that same year, he finally explained the odd movement Brown had observed nearly a century earlier. Einstein realized that the pollen grains were not moving by their own power. They were being pushed around by invisible forces. Tiny, individual water molecules, far too small to be seen, were constantly colliding with the pollen grains, making them jiggle. But how could something as minuscule as a water molecule have any effect on a pollen grain, which was a billion times heavier? Imagine standing in the middle of a massive concert crowd, surrounded by tens of thousands of people. As the crowd surges left and right, you have no choice but to move with them. Sometimes the pressure comes from one side, sometimes from another, and sometimes from all directions at once. Even though you try to hold your place, the endless random pushes make you sway back and forth, never quite standing still. This, Einstein realized, was exactly what was happening to the pollen grains. The water molecules were so numerous and so relentless in their collisions that they kept the grains in constant motion. And from his calculations, Einstein was able to do something extraordinary. He proved, with mathematical certainty, that water was made of tiny, invisible particles. In other words, he confirmed that atoms and molecules were real, physical things, not just abstract ideas. The birth of atomic physics. With Einstein's work, the atomic theory was no longer just a hypothesis, it was a fact. The world was built from these tiny, indivisible particles, or at least that's what scientists thought. But just as they were celebrating the discovery of atoms, new evidence emerged that shattered their understanding once again. In the year 1896, Henri Becquerel and Marie Curie discovered that certain elements, like uranium, could change spontaneously, breaking down into other elements and emitting strange, invisible rays. This was proof that atoms were not as unbreakable as once believed. Then, in the year 1897, J.J. Thomson made an even bigger breakthrough. He discovered the electron, a tiny particle hiding inside the atom itself. It was clear, atoms were not the ultimate, indivisible pieces of matter. Instead, they were complex structures with even smaller components inside. This realization set off a scientific race, one that would lead, decades later, to the moment when Walton and Cockcroft finally split the atom and unlocked the power hidden within. The man often called the father of nuclear physics, Ernest Rutherford, made a groundbreaking discovery in the early years of the 20th century. At the University of Manchester, he assigned two young researchers, Hans Geiger and Ernest Marsden, to investigate the structure of matter. Their task: to sit in a completely dark room, staring at a tiny screen, looking for the faintest flashes of light. These flashes appeared whenever tiny invisible particles, alpha particles, collided with a fluorescent surface. Up until that point, their experiment had gone exactly as expected. Hans Geiger, one of the researchers, would later become famous for the Geiger counter, a device used to detect radiation. But at the time, he was simply a dedicated scientist, patiently logging every single flash of light he saw. Day after day, he and Marsden counted thousands of these tiny bursts, recording each one with precision. Then, one day, Rutherford suggested something unusual. He asked them to check for flashes where none should appear. Following their mentor's instructions, Geiger and Marsden adjusted their experiment and stared once more into the darkness. What they found would change the way we understand the universe forever. Rutherford himself was stunned. At just 40 years old, he had already won a Nobel Prize, yet he called this discovery the most astonishing moment of his life. This single experiment would reshape science, altering our view of the very building blocks of reality. But what had they actually seen, and why did it matter? A few years earlier, a scientist named J.J. Thomson had discovered the electron, revealing that atoms contained negatively charged particles. Since atoms are electrically neutral, scientists reasoned that there must also be some kind of positive charge inside them. The big mystery was how these charges were arranged. Thomson proposed a model known as the plum pudding model. Imagine a traditional British fruitcake filled with raisins, except in this case, the cake represented a positively charged material, and the raisins were the negatively charged electrons suspended inside. Rutherford's experiment was designed to test this idea. He created a beam of alpha particles, tiny, positively charged fragments of atoms, and aimed them at an incredibly thin sheet of gold foil. If Thomson's model was correct, the alpha particles should have passed straight through or been slightly deflected, like bullets moving through fog. And at first, that's exactly what happened. Most of the particles sailed right through the gold, as if the atoms weren't even there. Some of them were deflected a little, just as Thomson's model predicted. But then came the shock. When Geiger and Marsden changed the way they observed the experiment, they saw something that should have been impossible. Some of the alpha particles bounced back, ricocheting at sharp angles, as if they had struck something incredibly solid. Rutherford was astonished. He later compared it to firing a heavy artillery shell at a sheet of tissue paper, only to have it bounce back and hit you in the face. This unexpected result proved that Thomson's model was wrong. The positive charge inside an atom wasn't spread out like pudding. It was concentrated in a tiny, dense core. This core, which Rutherford named the nucleus, contained nearly all of the atom's mass. The electrons, meanwhile, were incredibly small and occupied the space around the nucleus, but they barely had any mass at all. This meant something astonishing. Atoms, the fundamental building blocks of everything, are mostly empty space. The solid objects we see and touch, chairs, walls, trees, apples, are made of atoms held together by invisible forces, yet the majority of each atom is just empty space surrounding a tiny, powerful center. Rutherford's discovery opened the door to the field of nuclear physics, leading to further breakthroughs that would shape the modern world, from atomic energy to medical imaging. But it also revealed something deeper about our reality. The seemingly solid world around us is, in fact, built on an illusion of solidity, held together by forces we can barely comprehend. Have you ever stopped to think about what makes something solid? That apple sitting on your kitchen counter, your desk, even your own body. Everything seems firm and real. But the truth is, most of what you see and touch is actually empty space. The solidness you experience is just an illusion. And it's not just apples or furniture. It applies to everything, including you. That might sound unsettling, but maybe there's some comfort in knowing that even though atoms are mostly empty, they still contain something real. At the center of each atom is a nucleus, surrounded by tiny electrons whizzing around in orbits. Surely those pieces must be solid, right? They must truly exist. But just as scientists once thought the molecule was the most basic unit of matter, only to later discover the atom, they soon realized that even the nucleus itself was not as simple as it seemed. On the 10th of August in the year 1915, in the heat of World War I, a sniper took careful aim. He steadied his breathing, his finger gently squeezing the trigger. A single shot rang out. Birds scattered in the distance. His target crumpled to the ground. The sniper moved on, unaware that he had just ended the life of one of the greatest minds of the 20th century. The First World War claimed the lives of nearly 20 million people, both soldiers and civilians. Another countless number were wounded, their lives forever changed. Among those lost was Henry Gwyn Jeffreys Moseley, a young scientist who had been unraveling the deepest mysteries of the atom. Before enlisting as a soldier, a decision made out of a sense of duty, despite his family's strong objections, Moseley had been on the brink of a revolutionary discovery. Born in the year 1887 in Dorset, England, Moseley was the son of an Oxford professor and a brilliant student in his own right. He attended Oxford University before joining the renowned scientist Ernest Rutherford in Manchester in the year 1910. There, he began using X-rays to study elements, hoping to uncover the hidden secrets of their atoms. During his experiments, he noticed that different elements emitted X-rays at different energy levels, and he suspected that something deep inside the atom was responsible. Meanwhile, in the Netherlands, an amateur physicist named Antonius Johannes van den Broek had a bold idea. He knew that electrons, tiny particles carrying a negative charge, always seem to have the same mass and the same charge, no matter the element. So, what if the nucleus was made of separate, positively charged pieces, just like electrons? If atoms were electrically neutral, then these positive charges would have to balance out the negative ones. The only thing that would make one element different from another would be the number of these positive charges in the nucleus. Moseley realized that this idea perfectly matched what he was seeing in his experiments. The heavier the element, the more positive charges in its nucleus, and the more powerful the X-rays it emitted. With this discovery, he rearranged the periodic table, organizing elements by what we now call their atomic number, a system still used today. Years later, in 1962, the legendary physicist Niels Bohr would reflect on Moseley's work, saying, "You see, actually, Rutherford's work was not taken seriously. There was no mention of it in any place. The great change came from Moseley." But what else could Moseley have discovered, had his life not been cut short by that sniper's bullet in 1915? As the Great War raged on, the field of atomic science continued to advance. Once again, it was Ernest Rutherford, always at the forefront, who made the next great breakthrough. Through his research into radioactivity, he uncovered the true nature of the atom's structure. Hydrogen, the simplest element, had just one positive charge and a single electron. Helium had 2 positive charges and 2 electrons. Lithium had 3, beryllium had 4, and so on. Each of these positive charges was identical in both charge and mass. Rutherford gave them a name: protons. Then, in the year 1932, after years of speculation, another fundamental particle was finally confirmed through experiments: the neutron. With its discovery, the true structure of the atom was finally complete. What had once seemed impossibly complex had been simplified. The entire world, every material thing in existence, was built from just 92 natural elements, and each of those elements was made up of only 3 fundamental pieces: protons, neutrons, and electrons. At the outer edges of the atom, electrons move at speeds close to that of light, creating the illusion of solid matter. But at the very heart of the atom lies the nucleus, a compact, dense core made of protons and neutrons. This tiny center is where most of an atom's mass resides, the very foundation of all matter in the universe. And yet, for all its seeming solidity, it is still mostly empty space. When Ernest Rutherford introduced his groundbreaking idea of what atoms looked like, many scientists were excited, but others saw it as a disaster waiting to happen. His model of the atom had a serious problem, one that could shake the very foundations of physics. The issue stemmed from the work of James Clerk Maxwell, whose equations of electromagnetism described how electric charges behaved. According to these laws, any charged particle that moves in a curved path, like an electron orbiting the nucleus, should constantly give off energy in the form of electromagnetic waves. But if that were true, then an electron wouldn't be able to stay in its orbit for long. Instead, it would rapidly lose energy, spiral inward, and eventually crash into the nucleus. If Maxwell's laws were correct, then Rutherford's atom simply could not exist. And yet, atoms clearly did exist. Matter was stable, the universe had structure, and everything around us wasn't just collapsing in on itself. But there was no explanation for why. According to the established laws of physics at the time, the very idea of stable matter should have been impossible. Faced with this paradox, physicists had only one option. They had to rewrite the rules. They had to rethink reality itself. This shift would eventually give birth to an entirely new field of science, quantum mechanics, a discovery that would forever change our understanding of the universe. In the year 1943, the brilliant physicist Niels Bohr, one of the founding fathers of quantum mechanics, found himself in grave danger. The German government had declared that he and his family were Jewish, putting them at immediate risk of arrest. With time running out, Bohr turned to the Dutch resistance for help. Thanks to their bravery, he managed to flee to neutral Sweden, escaping the clutches of the Nazis. However, his journey was far from over. Word of his escape reached the British government, and they saw an opportunity. The Second World War had been raging for 4 relentless years, and the Allies were desperate for a new weapon, one so powerful it could end the conflict once and for all. They had decided that an atomic bomb was the key to stopping the devastation, and Bohr's deep knowledge of the subatomic world was invaluable. They could not allow such a mine to fall into enemy hands. Under a secret arrangement, Bohr was retrieved from Sweden. To conceal his identity, he traveled under the alias James Baker. His journey took him across the ocean and eventually to a top-secret location in the United States, a hidden town in the deserts of New Mexico known as Los Alamos. There, alongside some of the brightest scientific minds of the time, he contributed to the Manhattan Project, the effort that would lead to the creation of the atomic bomb. Despite his immense knowledge, Bohr humbly insisted that he wasn't essential to the project, believing the younger scientists had things well in hand. But Robert Oppenheimer, the project's director, strongly disagreed. According to him, the early days of quantum mechanics had been a time of great discovery and teamwork, involving brilliant minds from around the world. Yet, from the very beginning to the very end, it was Bohr's deeply creative and critical thinking that shaped, refined, and ultimately transformed the field. 3 decades earlier, in the year 1913, the world had been on the brink of another great war. At that time, Bohr's mind was not concerned with how to harness atomic power for destruction, but rather with an even deeper question. Why did atoms exist at all? The great physicist Ernest Rutherford had proposed a model of the atom, but it left an unsettling problem. According to the established laws of physics, electrons should spiral inward and collapse into the nucleus. But they didn't. Why? By the end of the 19th century, physics seemed almost complete, with only a few puzzling details left to resolve. But those small mysteries would turn the field upside down. Everything started with a simple question. Why do hot objects glow? It was common knowledge that when an object is heated, it begins to emit light. An iron rod placed in a fire first glows red, then white, and if made even hotter, it shifts to blue. But no one could explain why these specific colors appeared in that order. A German physicist named Max Planck, at the age of 42, took up the challenge. He tried every mathematical trick in the book, but nothing worked. Finally, at the peak of frustration, he did something radical. He rewrote the rules of physics. Planck proposed that energy did not flow continuously as previously thought. Instead, it came in small, distinct packets. He called these packets quanta. To his surprise, this bold idea perfectly explained the glowing colors of heated objects. At first, Planck believed he had merely found a clever mathematical shortcut. But then, in the year 1905, Albert Einstein extended this idea to explain another mystery: how light could knock electrons off metal surfaces. Einstein declared that light itself came in discrete chunks called photons. This revelation set off a revolution in physics. The idea of quantization, the notion that things existed in set, indivisible amounts, was appearing everywhere. Then came Rutherford's discovery that atoms had a dense, positively charged nucleus. But something still wasn't right. The rules that governed this tiny atomic world remained unknown. That is, until Bohr entered the picture. Bohr proposed a groundbreaking idea. Electrons could only occupy specific orbits around the nucleus, each with a fixed energy level. They could jump between orbits, but only if they absorbed or emitted the exact amount of energy needed to bridge the gap. Most importantly, there was a lowest possible orbit, one that prevented electrons from spiraling inward and collapsing the atom. This idea transformed physics. Bohr had saved the atom from destruction, and in recognition of his achievement, he was awarded the Nobel Prize in Physics in the year 1922. Yet, despite this success, scientists still struggled to understand why electrons followed these strange quantum rules. The answer came just 2 years later from a young French aristocrat and physicist named Louis de Broglie. He had been closely following the rapid developments in quantum theory and was struck by something peculiar. Light, which had always been considered a wave, sometimes behaved like a particle. If light could exist as both a wave and a particle, then why not matter as well? De Broglie proposed a radical idea. Electrons, too, had wave-like properties. They did not simply orbit the nucleus like tiny planets. Instead, they formed standing waves around it. These waves could only exist in certain patterns, which explained why electrons could only occupy specific energy levels. It was the Austrian physicist Erwin Schrödinger who turned de Broglie's idea into a powerful mathematical equation. Rather than picturing an electron as a tiny point moving around the nucleus, Schrödinger described it as a wave spread out over the entire orbit. Suddenly, Bohr's atomic model made perfect sense. The allowed orbits were simply those where the electron waves fit perfectly, reinforcing themselves rather than cancelling out. Today, the idea that quantum objects can behave both as particles and waves is widely accepted. But in the early 20th century, de Broglie's proposal shook the scientific world to its core. For his insight, he was awarded the Nobel Prize in the year 1929. By the 1930s, it seemed that the mysteries of physics had been unraveled. The entire periodic table of elements could be explained using just 3 basic building blocks: protons, neutrons, and electrons, governed by the principles of electromagnetism and quantum mechanics. But just when scientists thought they had everything figured out, new discoveries would once again turn the world of physics upside down. Back in the year 1929, an English physicist named Paul Dirac was deeply focused on unraveling the mysteries of quantum mechanics. He was determined to make quantum physics fit together with another major scientific theory, Albert Einstein's theory of relativity. After much effort, he finally created a new set of equations that seemed to bridge the gap between these two powerful ideas. However, as Dirac examined his own equations, he noticed something unexpected. Not only did they perfectly describe how electrons behaved, but they also hinted at something else, something that wasn't supposed to exist in the known atomic world. His equations predicted a strange new particle, a positively charged version of the electron. This was the first hint of what we now call the positron. At first, many scientists dismissed it. They thought it was just a mathematical quirk, a meaningless feature of the equations that didn't reflect reality. But that changed in the year 1932, when actual experiments proved that the positron was real. It was a groundbreaking discovery. But then, something even stranger showed up in particle experiments, a new particle that made even less sense than the positron. It behaved just like an electron, carrying the same negative charge, but there was one major difference. It was incredibly heavy. This new particle, called the muon, was about 200 times more massive than an electron. And unlike electrons, which are stable and last indefinitely, muons were extremely unstable. They vanished almost as soon as they appeared, decaying into other particles in just 2/1,000,000th of a second. This raised a huge question. Why did the muon even exist? It seemed completely unnecessary. The universe already had electrons. Why would nature create another, heavier version that didn't seem to serve any purpose? One frustrated physicist, Isidor Rabi, famously joked, "Who ordered that?" The discovery of the muon made it clear that the atomic world was far messier than scientists had hoped. As the years passed, things only got more chaotic. Throughout the 1940s and 50s, physicists kept finding more and more bizarre particles, each one stranger than the last. By the time the 1960s arrived, the world of particle physics was in complete disarray. There were so many different particles, it felt as if nature had no logical pattern at all. But then a breakthrough came. Scientists realized that all these particles were not truly fundamental. Instead, they were made up of even smaller building blocks, tiny, indivisible entities called quarks. This discovery led to what we now call the Standard Model of particle physics. According to this model, protons, neutrons, and most of the other known particles are actually made up of 6 different kinds of quarks, arranged into 3 families. The lightest quarks are called up and down. Then come the charm and strange quarks. Finally, the heaviest ones are top and bottom. These quarks combine in different ways to form various particles. For example, protons are made of 2 up quarks and 1 down quark, while neutrons are made of 2 down quarks and 1 up quark. Other, more exotic particles exist as well, formed by different combinations of quarks. But quarks aren't the only key players in the subatomic world. There is also a family of particles called leptons, which includes the electron, the heavier muon, and an even more massive cousin called the tau. Each of these particles also has a ghostly companion known as a neutrino. So, the ordinary matter that makes up our world, the air we breathe, the food we eat, and even our own bodies, is primarily built from just a few of these particles, electrons and the up and down quarks inside protons and neutrons. Yet, the deeper we look, the stranger reality becomes. Unlike everyday objects, these fundamental particles don't have a definite size. They are point-like, meaning they take up no space at all. In a way, this means that the protons and neutrons inside your body are mostly empty. In fact, atoms themselves are overwhelmingly empty space, an idea that had already shocked scientists back when Ernest Rutherford discovered it. But quantum physics takes it even further. It turns out that even the tiny particles we think of as solid objects are not truly solid at all. Instead of behaving like little balls, quantum particles act like waves, spread out across space, existing everywhere and nowhere at once. So, when you look at something as ordinary as an apple, what are you really seeing? The apple appears solid, yet at the subatomic level, it is mostly empty space. And even the particles that make it up aren't truly things in the way we imagine. Instead, they are shifting, fluctuating waves of energy, dancing in an unseen quantum sea. This leads to one of the deepest questions in science. What exactly are these waves? And what is it that's actually waving? Could it be that the entire reality we experience is nothing more than a vast ocean of invisible quantum waves? Imagine you're in your kitchen, preparing to bake a delicious cake. You gather your ingredients and start following the recipe, step by step. At one point, you realize you need a couple of eggs, so you walk over to your fridge. When you open the door, you see that the eggs are neatly arranged in their designated spots, some spaces filled while others remain empty. You take what you need, close the fridge, and continue baking without giving a second thought to the eggs you left behind. In your mind, there is no doubt that when you open the fridge again, the eggs will still be in the exact same spots. After all, how could it be any different? But modern science tells us that reality is far stranger than it seems. Let's replace the eggs in this scenario with tiny particles called electrons. Just like eggs in a fridge, electrons can be arranged in different positions. However, thanks to a revolutionary discovery in the early 20th century known as quantum mechanics, scientists learned that electrons do not behave in the predictable way we expect from everyday objects. Unlike the classical laws of physics discovered by Sir Isaac Newton, which describe how large objects move and interact, quantum mechanics shows us that electrons don't have fixed positions. Instead of saying, "This electron is right here," scientists can only describe the probability of finding an electron in a certain place. It's as if the electron exists in multiple locations at once, only choosing a specific spot when we actually observe it. Now, let's return to our eggs. In theory, according to quantum mechanics, an egg in your fridge has a very tiny chance of suddenly appearing in a different hole without moving through the space between. This bizarre behavior is called quantum tunneling. However, for large objects like eggs, the probability of this happening is so incredibly small that you would never notice it in your lifetime, or even over the entire history of the universe. Still, the laws of quantum mechanics say it is possible. In the quantum world, reality is governed by probabilities rather than certainties. This shift in understanding was part of what scientists call the quantum revolution, which changed the field of physics forever in the early 20th century. Some of the greatest minds in science, including Albert Einstein, struggled with the strange implications of this new way of thinking. The debate over quantum mechanics began in the year 1926, when a physicist named Max Born proposed a groundbreaking idea. The previous year, another scientist named Erwin Schrödinger had developed an equation to describe tiny particles like electrons, but he was unsure about what his equation truly meant. Born suggested that Schrödinger's equation described waves, not waves of physical matter, but waves of probability. These probability waves could explain why electrons sometimes acted like tiny particles and sometimes behaved like waves. This idea helped solve a long-standing mystery. When scientists conducted experiments with electrons, they saw that electrons would hit detectors as tiny, distinct particles. However, in other experiments, electrons spread out like waves, creating patterns of interference, just like waves in water. To Born, this meant that electrons traveled as waves, but collapsed into definite particles when measured. To test this theory, scientists set up an experiment similar to an older one from the early 19th century, known as the double-slit experiment. In that classic experiment, light was shone through two slits, creating an interference pattern that proved light behaved like a wave. If electrons were truly quantum waves, scientists expected to see the same interference pattern. They fired a beam of electrons at a surface covered in regularly arranged atoms, expecting the electrons to bounce off randomly like tiny bullets. Instead, they found something incredible. The electrons formed an interference pattern, just as waves would. This proved that quantum objects, like electrons, were behaving as waves while traveling, but as particles when detected. To grasp how strange this is, imagine you are an Olympic sharpshooter aiming at a target 100 meters away. You line up your shot, hold your breath, and pull the trigger. Normally, your bullet would travel in a straight line toward the target. But if you were in a quantum world, the bullet would spread out like a wave, passing around corners, interfering with other bullets, and landing in unexpected places. Instead of a precise impact, you would see a strange interference pattern on the target. This strange mix of behaving both as a particle and as a wave is known as wave-particle duality. While we do not see these effects in our daily lives, scientists have observed quantum interference patterns even in large molecules made of dozens of atoms. This suggests that quantum behavior is not just a small-scale phenomenon, but something deeply woven into the fabric of the universe. Today, we harness the power of quantum mechanics in some of our most advanced technologies. For example, electron microscopes use beams of electrons instead of light to magnify objects. Since electrons have wave properties, they can reveal details far smaller than what ordinary microscopes can see. This has led to breakthroughs in fields like medicine, nanotechnology, and materials science. Although quantum mechanics has been tested and proven through countless experiments, it still raises many mind-boggling questions. Why do we not experience quantum effects in our daily lives? What causes a quantum wave to collapse into a particle when measured? The quantum world is full of mysteries, and even after more than 100 years of study, scientists are still searching for answers. In the year 1954, Max Born received the Nobel Prize for his work in quantum mechanics. This happened just 1 year before the great Albert Einstein passed away. However, in the many years between Born's groundbreaking achievements and Einstein's final days, the two brilliant minds found themselves at odds over the true nature of reality. Einstein, despite being friends with Born, could never accept the idea that the universe was governed by probability. He strongly believed that the universe must follow strict, unbreakable rules, a system where everything had a definite cause and effect. While he acknowledged that quantum mechanics used probabilities to describe the behavior of tiny particles, he was convinced that there had to be a deeper, hidden order beneath it all. In a now famous letter to Born, Einstein expressed his skepticism in a simple but powerful way. "I, at any rate, am convinced that God is not playing at dice." By the time he wrote this, in the year 1935, Einstein had already left his home country of Germany due to rising political tensions and had settled in the United States. It was there that he formulated an argument against quantum mechanics, a thought experiment designed to expose what he believed were its fundamental flaws. This idea became known as the EPR paradox, named after its three authors, Einstein, Podolsky, and Rosen. Even though it was introduced nearly 100 years ago, the paradox remains a crucial part of modern discussions about the strange and mysterious nature of the quantum world. At the core of this paradox was a phenomenon that troubled Einstein deeply, something that seemed to defy the very laws of physics. According to quantum mechanics, when two particles are created together, they share a mysterious connection, no matter how far apart they travel. This concept, known as quantum entanglement, suggested that measuring one particle could instantly affect the other, even if they were separated by enormous distances, perhaps even light years apart. To illustrate this, imagine two tiny particles being formed through a mysterious event. The details of the event don't matter, but what does matter is that these two particles end up with linked properties. Let's say they are created with opposite quantum spins, one spinning upwards, the other spinning downwards, ensuring that their total spin remains balanced at zero. However, according to quantum mechanics, their exact states are not determined until they are observed. Instead, each particle exists in a strange limbo where it has a 50% chance of spinning upwards and a 50% chance of spinning downwards. Now, imagine these two particles drift apart, traveling across the universe as probability waves. For a long time, nobody knows their exact states. They exist only as possibilities. Then, suddenly, one of them encounters a spin detector. The moment the detector registers the spin direction, the mystery is solved. If the first particle is found to be spinning upwards, The other one, no matter how far away, must be spinning downwards. But this is where the real puzzle begins. How does the second particle know what happened to its twin? Did the wave function collapse instantly, across vast distances, at speeds faster than light? If so, this would go against Einstein's special theory of relativity, which states that nothing in the universe can travel faster than the speed of light. Einstein saw this as a major problem. He believed this strange, instant communication between particles was proof that quantum mechanics was incomplete. He argued that beneath the apparent randomness of quantum physics, there had to be a deeper layer of reality, one governed by hidden variables that determined outcomes with certainty. In other words, Einstein was convinced that we simply hadn't discovered the full picture yet. For years, scientists searched for these hidden variables, hoping to restore a sense of order and determinism to the quantum world. Einstein, along with the physicist Louis de Broglie, proposed new theories, only to abandon them later. Others attempted to refine the EPR paradox, trying to reconcile it with Einstein's belief in a predictable universe. However, by the 1960s, their hopes were shattered by the groundbreaking work of an Irish physicist who would forever change our understanding of quantum reality. John Stuart Bell was born in the city of Belfast in the year 1928. From a very young age, he was fascinated by the mysteries of the universe and dreamed of becoming a scientist. That passion led him, by the time he reached adulthood, to a career as a theoretical physicist. By the year 1960, Bell had made his way to the border between Switzerland and France, where he joined the newly established European Organization for Nuclear Research, better known as CERN. Bell made several groundbreaking contributions to physics, particularly in the study of reality at the quantum level. However, he is best remembered for something known as Bell's inequalities. His work was an extension of an earlier thought experiment called the EPR paradox, but he introduced a crucial and insightful twist. The EPR paradox, originally proposed by Albert Einstein and his colleagues, describes what happens when a pair of quantum particles become entangled. When these particles separate, even across vast distances, their properties remain mysteriously linked. Each particle is sent toward a detector that measures whether it spins in one direction or another, either up or down. If one detector registers a spin in the up position, the other will always register down. If the first detector records a sequence of up, up, down, 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 the second must show the exact opposite, down, down, up, up, up. These results are perfectly correlated, but Bell wanted to push this idea further. He asked, what if the two detectors were not aligned in the same direction? What if one detector measured up and down, but the other was rotated to measure left and right instead? At first, this might sound like a strange thing to do. After all, if a particle spins either up or down, how could it possibly have a spin in the left or right direction? However, thinking this way means imagining particles like tiny solid balls spinning in a well-defined way, much like marbles. But in the quantum world, things do not behave like classical objects. Instead, they exist as probability waves, meaning there is some chance a particle will register as up or down, and another chance it will register as left or right. This is where things start to defy common sense, but it is also the way nature works at the smallest scales. Bell began to analyze what the pattern of correlations between the two detectors should look like. If the particles had hidden variables, that is, if they carried some kind of secret instructions that determined their behavior in advance, then the results would follow a predictable pattern. But if there were no hidden variables, if reality was purely quantum and probabilistic, then a completely different pattern would emerge. This led to a race among physicists to put Bell's theory to the test. It did not take long before the first experiments were carried out. Scientists heated calcium atoms inside a special oven until they emitted pairs of entangled photons. These photons then traveled toward two separate detectors, where their polarization, The direction of their electric fields was measured. If the photons contained hidden variables, the measurements should have matched a certain expected pattern. But if the photons were governed purely by quantum mechanics, a different set of correlations should appear. The results left no room for doubt. The predictions of hidden variable theories did not match what was observed. Reality, it seemed, was not made up of definite properties, but was instead spread out over quantum waves. More experiments in the following decades only confirmed this shocking conclusion. The idea that the universe worked in a purely deterministic way, a belief Einstein held dearly, had to be abandoned. Now, you might be wondering, what does all of this mean for the real world? It might seem like an obscure academic debate, something that only matters to physicists working in specialized laboratories. But the implications are enormous. One of the most fundamental principles in physics has always been locality. This means that objects and forces should only be affected by what is happening in their immediate surroundings. If you push an object, it moves because of the force you applied directly to it. It does not respond to a force acting on another object millions of miles away. But quantum mechanics does not follow this rule. A measurement taken on one particle in one part of the universe can instantly affect another particle located far away. This strange, counterintuitive phenomenon was something Einstein himself could never accept. In a letter written in the year 1947 to physicist Max Born, he famously called it spooky action at a distance. And yet, no matter how much Einstein disliked the idea, experiments have shown that this bizarre behavior is real. When we zoom in on the tiniest building blocks of the universe, we find that no particle exists entirely on its own. Everything, at some level, is connected to something else. This might sound unbelievable. After all, how could something as ordinary as an apple in your hand be entangled with other particles scattered across the cosmos? It seems absurd, but the truth is, the universe does not care about what seems logical or intuitive to us. It follows its own strange rules, whether or not we can easily understand them. In recognition of the profound impact of Bell's work, the Nobel Prize in Physics in the year 2022 was awarded to 3 physicists, Alain Aspect, John Clauser, and Anton Zeilinger. Over decades of experiments, they confirmed again and again that particles, even when separated by vast distances, behave as if they are part of a single, interconnected system. Their work ruled out any lingering possibility that hidden variables could be controlling the outcome behind the scenes. One of the most extreme experiments ever conducted was called the Cosmic Bell Test. Scientists had long worried that earlier tests might not be truly independent. Every experiment is built using atoms, and those atoms have existed for a long time. What if, over the course of history, the atoms in the experiment had already interacted with each other in ways that skewed the results? And beyond that, what about the physicists themselves? The human experimenters setting up these tests are also made of atoms. Atoms that have existed for billions upon billions of years, taking part in countless interactions across the universe. Physicists like to think of themselves as neutral observers, standing apart from the experiments they conduct. They assume their laboratory equipment is isolated, unaffected by outside influences. But in reality, everything is interconnected. The equipment, the scientists, even the very particles they are measuring. All of it has a deep, shared history stretching back to the birth of the universe itself. Bell's work and the experiments that followed showed us something profound. At the deepest level, reality is not as straightforward as it appears. The universe is not made of separate, independent objects, but of things that are entangled across space and time. No matter how far apart they may be, they remain connected in ways that defy common sense. And that, perhaps, is the most astonishing discovery of all. Over the course of billions of years, atoms have had countless chances to mix, collide, and interact in ways we can hardly imagine. With each of these interactions, any hidden influences they might have carried could have been altered, rewritten, or linked together in complex ways. This raised an interesting possibility. What if the strange connections physicists observe between particles weren't due to the nature of reality itself, but simply the result of atoms having a long and tangled history? In other words, instead of proving that reality was deeply interconnected in a mysterious way, these correlations could just be a byproduct of atoms' shared past. This opened up a major challenge for scientists. They wondered, could there be unseen forces at work, making it seem like quantum entanglement existed when, in reality, it didn't? If so, their experiments might have a hidden flaw, one that physicists call a quantum loophole. To rule this out, they needed to ensure that their tests weren't being influenced by anything within our world. They needed a source of randomness, something beyond human interference, beyond Earth itself. So, they turned their gaze to the vastness of space. As they set up their experiment in the usual way, they introduced a new element, the light from two distant stars. The tiny flickers in this ancient starlight were completely natural, shaped by cosmic forces billions of years ago. These random fluctuations determined how the experiment was conducted, setting the angles at which the properties of the particles were measured. The results were astonishing. Yet again, they confirmed that reality does not behave in a strictly local way. Something beyond our conventional understanding was at play, but the physicists weren't done yet. To push the test even further, they decided to use light from quasars, some of the oldest and brightest objects in the universe. These distant beacons sent their light across nearly 8 billion years of time and space before it reached us. By using the unpredictable flickers of quasar light to guide their experiment, scientists eliminated even the tiniest chance that some hidden factor could have influenced their measurements. The outcome remained unchanged. Quantum entanglement was real, and reality itself was undeniably non-local. This discovery challenges the way we see even the most ordinary things. Imagine an apple sitting on your table. It looks solid, real, and right there in front of you. But at its core, it is made of particles. Particles that are not only connected to each other, but possibly entangled with other particles spread throughout the universe. This means that, in some strange way, the apple is not just an object on your table. It is part of something far greater, mysteriously intertwined with the cosmos itself. And so, a deeper question arises. Why? What invisible rules link every particle, every atom, every star? What is the hidden structure that connects everything in existence? The answer, whatever it may be, lies at the heart of the universe itself. On the 18th of April in the year 1955, an old man took his last breath. He had come into this world nearly 80 years earlier in Germany, but his final moments unfolded in an American hospital. His last words were spoken in his native German tongue, but their meaning is lost to history because the nurse by his side did not understand the language. In the final hours of his life, he made 3 simple requests: his glasses, his writing tools, and the equations he had been working on. Even as the end approached, his mind remained focused on solving one last mystery. This man, Albert Einstein, is remembered as one of the greatest physicists to ever live, his name forever etched into the pages of science textbooks. However, in the later years of his life, his attention had turned to a single profound question, a question that continues to puzzle physicists even today. At the beginning of the 20th century, 2 groundbreaking theories reshaped our understanding of the universe. One was Einstein's theory of relativity, which explained gravity and how it shapes the vast cosmos. The other was quantum mechanics, a theory that described the bizarre behavior of tiny particles at the subatomic level. Over the decades, quantum mechanics evolved into what scientists now call quantum field theory. This theory tells us that invisible fields stretch across all of space, and within these fields, waves ripple and create the fundamental building blocks of our universe, particles like electrons and quarks. One of the most important achievements in modern physics is the Standard Model of particle physics. This model explains how these quantum fields interact. For instance, when two charged particles, such as electrons, get close to one another, they send ripples through the electromagnetic field. These ripples create particles of light known as photons, which act as messengers of the electromagnetic force. Even the electrons themselves are just waves within the electron field. In the same way, quarks, the tiny components that make up protons and neutrons, are simply vibrations in their own unique fields. Beyond the electromagnetic field, there are other forces at play in the universe, each with its own field and particles. The strong nuclear force is what keeps quarks bound tightly together inside protons and neutrons, and it also holds atomic nuclei intact. The vibrations in this strong force field create particles called gluons, which act like glue, keeping everything together. Then there is the weak nuclear force, which plays a key role in certain types of radioactive decay. The vibrations in the weak force field produce particles known as W and Z bosons, which mediate this force. To truly grasp how quantum fields govern our universe, let's consider a neutron, a particle found in the nucleus of an atom. If a neutron is left on its own, it does not remain unchanged forever. Within roughly 15 minutes, it will undergo a transformation. It turns into a proton while releasing an electron and a nearly undetectable particle called a neutrino. But what is really happening at the quantum level? A neutron is made up of 3 quarks, 2 down quarks and 1 up quark. These quarks are constantly interacting with the strong force field, sending out and absorbing gluons that keep the neutron stable. However, the weak force is also present, and at some point, one of the down quarks will interact with it. This triggers a change. The down quark transforms into an up quark, turning the neutron into a proton. In the process, a W- boson is created, but it exists for only a fleeting moment, less than a billionth of a second, before it vanishes, leaving behind an electron and a neutrino. Every interaction between quantum particles follows this same fundamental pattern. Fields ripple, particles emerge, forces act, and the universe continues to unfold according to these invisible laws. And though Einstein dedicated his final years to understanding how all these forces could be unified into a single grand theory, the answer to that mystery remains unsolved to this day. There is one more quantum field that plays a crucial role in shaping our understanding of the universe, perhaps the most famous of them all, the Higgs field. This invisible energy field exists everywhere in space, and its interactions are what give mass to fundamental particles. The disturbances, or ripples, in this field create a particle known as the Higgs boson, which was finally discovered in the year 2012 after scientists had searched for it for more than 40 years. The story of the Higgs field begins in the early 1960s when physicists encountered a puzzling problem. They knew that the weak nuclear force, the force responsible for radioactive decay, was linked to 2 particles called bosons, named the W and Z bosons. However, according to quantum field theory, the force-carrying particles of nature, like photons for electromagnetism and gluons for the strong nuclear force, should have no mass. But strangely, the W and Z bosons were heavy. This was a big problem because just adding mass to these particles in mathematical equations caused the calculations to break down, spiraling into infinities. It became clear that something else was needed, some new mechanism that could explain how these particles got their mass. That's when the Higgs field came into the picture. This energy field fills all of space, and when particles like the W and Z bosons move through it, they interact with the field in a special way, gaining mass. Meanwhile, other particles, like photons and gluons, do not interact with the Higgs field at all, which is why they remain massless. But the Higgs field wasn't just a solution for the W and Z bosons. It turned out to be much more powerful. Scientists soon realized that the same mechanism that gave mass to these weak force particles could also explain why all fundamental particles, including electrons and quarks, have mass. As these tiny particles travel through what seems to be empty space, the Higgs field ensures that they acquire the right amount of mass, allowing the universe to exist as we know it. Quantum field theory has proven to be one of the most successful scientific frameworks in history. It can predict, with incredible accuracy, the results of experiments involving subatomic particles. It explains the behavior of electrons, quarks, and even sprays of energetic particles called gluons. On the other hand, Albert Einstein's theory of relativity has been just as successful in explaining how planets, stars, and galaxies move through space. However, the incredible precision of both of these theories also highlights a major problem: Einstein's biggest headache. While he didn't have access to the detailed understanding of fundamental forces that we have today, he recognized that something wasn't right. General relativity describes gravity as the bending and warping of space and time, while quantum field theory explains nature in terms of probabilities and waves. These two descriptions seem to speak completely different languages. At first glance, this might not seem like a big deal. If gravity and quantum mechanics require two different sets of mathematics, why should it matter? But for Einstein and many other physicists, this was an unacceptable contradiction. The ultimate goal of modern physics has always been to unify all forces into a single, elegant framework, a theory of everything. This dream of unification started in the 19th century with James Clerk Maxwell, who showed that electricity and magnetism were not separate forces, but two aspects of the same thing: electromagnetism. With the arrival of quantum field theory, things became even more streamlined. Scientists found that three of nature's fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, could all be explained using the same mathematical language. It seemed like the universe was built on a beautifully simple foundation. Except for one glaring issue: gravity did not fit. As soon as general relativity was introduced, physicists began wondering if the answer could be hidden in extra dimensions. What if space and time had more than just the three dimensions we see around us, more than up-down, left-right, and front-back? What if these extra dimensions contained the forces of nature? Some early theories suggested that this could work, but they weren't perfect, and they raised a huge question. If these extra dimensions exist, why don't we see them? Physicists came up with a clever idea. What if these extra dimensions were curled up so tightly that they were too small for us to detect? Imagine trying to put together a Lego set while wearing thick boxing gloves. You wouldn't be able to grasp the small pieces. Similarly, these extra dimensions could be coiled up so minutely that we have no way of perceiving them in everyday life. For many decades, these ideas remained on the fringes of physics. But in the 1960s, something changed. Scientists realized that these curled-up dimensions could potentially explain all the fundamental forces of nature if they made one bold assumption. Instead of treating fundamental particles as tiny points, what if they were actually tiny vibrating loops of energy, or strings? This was the beginning of string theory. By the 1980s and 1990s, many physicists were convinced that string theory was the right path. They believed that any day now, someone would crack the incredibly difficult mathematics and the final piece of the puzzle would fall into place. However, as they continued their work, they found that their theory required more than 20 dimensions to function properly. The deeper they went, the more complex it became, and the long-awaited breakthrough remained out of reach. In more recent years, string theory has evolved into something called M-theory. The M in M-theory was left deliberately vague by its creator, physicist Edward Witten, because its full meaning remains unknown. In M-theory, tiny vibrating strings are replaced with higher dimensional objects called membranes, or brains. Some believe this could be the key to unification, but in reality, M-theory is still a work in progress, a loose collection of mathematical ideas searching for a final form. Not everyone is convinced by string theory, and some physicists have explored other ideas. One alternative is called loop quantum gravity, which suggests that space and time itself are made of tiny, discrete building blocks, much like pixels on a screen. However, this idea is also mathematically challenging and has yet to prove itself as a complete theory. New mathematical ideas are constantly being suggested and tested by scientists. However, most of these ideas eventually turn out to be incorrect. To navigate through this complex search for truth, physicists rely on one of the most fundamental principles in science, something that comes remarkably close to being the ultimate law of the universe. This concept is called symmetry. When we hear the word symmetry, we often think of things that look balanced and visually pleasing, like a beautifully designed building or a perfectly shaped vase. But symmetry is much more than that. It plays a crucial role in the language of mathematics and physics. The presence of symmetry in nature influences the very fabric of reality itself. To understand symmetry in a more mathematical way, let's take an example: a sphere. A sphere is a shape that can be defined precisely using mathematics. If you rotate a sphere in any direction, it still looks exactly the same. This is an example of rotational symmetry, a transformation that does not change the sphere's appearance. Scientists use mathematical tools to search for similar symmetries in physics, and these symmetries often lead to deep discoveries about how the universe operates. In the year 1915, a brilliant mathematician named Emmy Noether made an astonishing discovery. She showed that every symmetry in nature is linked to a fundamental law of conservation. But what does this actually mean? Let's imagine a simple physics experiment: rolling balls down a slope. Suppose you spend a lot of time carefully rolling these balls and measuring their speeds. Now, imagine moving your entire experiment 1 meter to the left or right and repeating the same process. Would you expect the results to be different? Of course not. The outcome would remain the same. This tells us that shifting the experiment sideways does not affect the results, meaning there is a symmetry in space. But what does this symmetry reveal? Noether's mathematics tells us that this kind of symmetry is directly linked to the concept of momentum conservation. In simple terms, momentum, which is mass times velocity, cannot just disappear. It must be transferred from one object to another. This is why, when one billiard ball strikes another, the energy is passed along rather than vanishing into thin air. There are many other symmetries in physics, each leading to its own conservation law. For example, if you rotate the entire experiment by 90 degrees and still get the same results, that symmetry is linked to the conservation of angular momentum, which is responsible for the spinning motion of planets, galaxies, and even everyday objects like spinning tops. But perhaps the most fascinating symmetry of all is related to time. Imagine performing your experiment today, then doing the exact same test tomorrow. You would expect to get the same results. This time, symmetry leads to one of the most fundamental rules in all of physics: the conservation of energy. This means energy cannot be created or destroyed, it can only change forms. Symmetry is woven deeply into the theories that shape our understanding of the universe. Einstein's theory of special relativity, for example, is built entirely on symmetries. In fact, these symmetries are what demand that nothing can travel faster than the speed of light. But it is in the strange world of quantum physics that symmetries truly dominate. Scientists discovered that electromagnetism, the force responsible for electricity and magnetism, follows a specific type of symmetry called U1. Other, more complex symmetries describe the strong and weak nuclear forces, the forces that hold atoms together and allow nuclear reactions to happen. With each of these symmetries comes a special quantity that must be conserved. For example, in electromagnetism, the conserved quantity is electric charge. But in other forces, entirely new and unfamiliar numbers appear, such as isospin, lepton number, and quark numbers. These seemingly abstract values actually govern what is and isn't possible in the universe. If a conservation law is obeyed, an interaction between particles can happen. But if the law is broken, the interaction is strictly forbidden. At the deepest level, reality itself seems to be built entirely on symmetries. Scientists, in their quest to uncover the fundamental nature of existence, have tried to find even deeper symmetries. One of the most ambitious ideas is called supersymmetry. This theory suggests that every fundamental particle we know has a superpartner, a heavier twin that has yet to be discovered. For example, an electron would have a selectron, a photon would have a photino, and so on. Supersymmetry, if proven true, would make the standard model of physics even more elegant and complete. Some researchers believe that this is the key to understanding the ultimate nature of reality. However, despite many experiments, scientists have not yet found any evidence of supersymmetric particles. Because of this, some believe that the theory may be wrong. But the search does not end there. The idea of symmetries remains central to other groundbreaking theories, such as string theory, M-theory, and loop quantum gravity. Some physicists believe that the key to understanding everything lies in a powerful mathematical idea known as anti-de Sitter, conformal field theory correspondence, or simply ADS-CFT. This fascinating concept, first introduced by an Argentinian physicist named Juan Maldacena in the late 1990s, suggests that our universe may be connected to a deeper reality through hidden symmetries. Scientists have discovered a fascinating mathematical connection between two different kinds of theories, one that explains gravity and another that describes the tiny particles making up our universe. This connection suggests something astonishing. The math describing a four-dimensional universe that has no gravity but is completely governed by quantum mechanics can perfectly match the math of a five-dimensional universe where gravity exists. In simple terms, gravity and quantum mechanics, two of the most important forces in nature, appear to be linked in a deep and fundamental way. For years, scientists have been trying to figure out what this connection really means. Could it be a hidden clue pointing toward a long-sought theory of everything? A single equation that explains how the entire universe works? Or could this discovery reveal something even stranger? One of the most mind-boggling ideas that comes from this research is that our reality might be a kind of hologram. You may have seen an optical hologram before, an image that looks three-dimensional but is actually stored on a two-dimensional surface. The same principle might apply to the entire universe. What if everything we experience, everything we see and touch, is just a projection from a lower dimensional space? In other words, what if our reality is like an illusion, similar to a holographic image? This idea, known as the holographic principle, originally came from the study of black holes. Black holes are some of the simplest objects in the universe because they can be completely described by just three properties: their mass, their spin, how fast they rotate, and their electric charge. Other than these three things, a black hole seems to forget everything about the objects that fall into it. But this presents a problem. In physics, one of the most important rules is that information can never be truly lost. It can change form, but it must always exist in some way. So, if a black hole swallows up all this information, where does it go? For a long time, scientists believed that the information was simply hidden deep inside the black hole, locked away forever. But in the early 1970s, a brilliant young physicist named Stephen Hawking shattered this idea. He realized that when you apply the rules of quantum mechanics to a black hole, something unexpected happens. It starts to emit tiny particles. These particles, now called Hawking radiation, slowly carry away the black hole's mass, causing it to shrink over time. Eventually, if given enough time, a black hole would completely disappear. This led to an even bigger mystery. If the black hole vanishes, what happens to all the information it once contained? It seemed like the information had been completely erased from existence, but that went against the fundamental rules of physics. Scientists began looking for a new explanation, and one idea gained serious attention. What if, instead of being lost inside the black hole, The information was actually stored on its outer boundary, called the event horizon. This means that as matter falls into a black hole, its information might be imprinted onto this two-dimensional surface, just like a hologram. Then, as the black hole evaporates, that information might be gradually transferred to the escaping radiation. If this is true, then black holes are not really three-dimensional objects in the way we think of them. Instead, they act more like a three-dimensional illusion, with all their information encoded on a flat, two-dimensional surface. And if this is true for black holes, then some scientists have suggested that our entire universe might work in the same way. That is, everything we see as three-dimensional, planets, stars, even our own bodies, might actually be information stored on a much simpler, lower-dimensional structure. This mind-blowing idea, if proven correct, would completely change our understanding of reality. But before we leave this discussion of symmetry and the universe, there's one more mystery to consider. The universe, as strange and complex as it is, does not have perfect symmetry. In fact, if it did, life as we know it would not exist. Consider the case of matter and antimatter. Our universe is filled with electrons, tiny particles that orbit around atoms and make up all the matter we see. But electrons have an opposite counterpart called positrons, which belong to a strange type of matter known as antimatter. The puzzling thing is that positrons are incredibly rare. In the Milky Way galaxy, scientists estimate that for every positron, there are more than 1 quadrillion. That's a 1 followed by 15 zeros, electrons. This raises a huge question. Where did all the missing positrons go? If the laws of physics were perfectly symmetrical, there should be equal amounts of matter and antimatter in the universe. But instead, we see far more matter than antimatter. Why did the universe evolve this way? The answer to this question could reveal one of the deepest secrets of the cosmos and possibly unlock new laws of physics that we have yet to discover. Imagine the universe in its earliest moments, right after its explosive birth, the Big Bang. At that time, the building blocks of everything we see today were forming. If the laws of physics were completely balanced, then matter and its opposite, antimatter, would have been created in equal amounts. This means that for every tiny electron that came into existence, a matching particle called a positron, its antimatter counterpart, would also appear. Now, here's where things get strange. When matter and antimatter meet, they destroy each other in a powerful burst of energy, leaving behind nothing but a sea of radiation. If nature had been perfectly symmetrical, then every single particle of matter would have been wiped out by its antimatter twin. The result? A universe with no atoms, no stars, no planets, no life at all. Everything would have faded into a cold, empty expanse of nothingness. But that's not what happened. Instead, something broke this perfect balance, a tiny, almost unnoticeable difference in the way matter and antimatter were formed. For every 1 billion annihilations, just one extra electron remained. This tiny, almost invisible imbalance also applied to protons and neutrons, which are the particles that form atoms. Instead of being completely erased, this leftover matter became the foundation of everything: the stars in the sky, the planets that orbit them, and even us. Physicists still don't fully understand why this happened. Somewhere, hidden in the fundamental laws of physics, there is a missing piece to the puzzle. Scientists have yet to uncover the precise reason for this break in symmetry. Some believe that solving this mystery may require a theory of everything, a single all-encompassing framework that explains every force and particle in the universe. However, even though the exact cause remains unknown, scientists have found important clues. One of them comes from a force that behaves unlike any other: the weak force. Among the fundamental forces of nature, gravity, electromagnetism, and the strong nuclear force, the weak force is the odd one out. While the other forces treat matter and antimatter the same way, the weak force does not. It actually favors matter over antimatter in a way that seems to defy logic. To understand why this matters, Let's take a closer look at the simplest atom in the universe, hydrogen. A hydrogen atom consists of a positively charged proton at its core with a negatively charged electron orbiting around it. When the electron moves between energy levels, it absorbs or emits light in a specific, predictable pattern. Now, imagine an atom of antihydrogen. Instead of a regular proton, it has a negatively charged antiproton. Instead of an electron, it has a positively charged positron. When the positron moves in its orbit, it emits or absorbs light in exactly the same pattern as a normal hydrogen atom. This tells us something important. Electromagnetism is completely symmetrical. It treats matter and antimatter the same way. The same is true for the strong nuclear force, which holds atomic nuclei together, and even for gravity. But the weak force is different. It does not follow this pattern. The results of its interactions change depending on whether it is dealing with matter or antimatter. This strange difference is connected to one of the universe's most mysterious particles, the neutrino. Neutrinos are incredibly elusive. They barely interact with anything, making them difficult to detect. But they have one very unusual property. They all spin in the same direction. In the quantum world, spin is a fundamental characteristic of particles. It doesn't mean they physically rotate like a planet, but it determines how they behave. For example, light particles, called photons, can have either a right-handed or left-handed spin, but neutrinos are different. Every single neutrino in the universe has a left-handed spin. Meanwhile, their antimatter counterparts, called antineutrinos, are all right-handed. This built-in difference between neutrinos and antineutrinos is what causes the weak force to behave in an asymmetric way. But why does the universe prefer left-handed neutrinos? Why does the weak force distinguish between left and right when no other fundamental force does? These questions remain unanswered. However, what scientists do know is that this tiny crack in the laws of physics, the break in symmetry, was absolutely necessary for our existence. Without it, matter and antimatter would have completely destroyed each other in the first moments of the cosmos, and the universe as we know it would never have formed. We have come a long way in our journey to understand reality. We've explored the hidden rules of quantum fields, the strange ways in which space can bend and twist, and the mysterious cracks in the symmetry of nature. But there is still one final puzzle that truly reveals how bizarre the quantum world can be when we follow its rules to their limits. Take a moment to look up at the night sky. The light from distant stars travels across millions of light years to reach your eyes. The way this light is detected is fascinating. Electrons in your eyes exchange photons with electrons that originated from those faraway stars. But how do these electrons know to exchange photons and experience the force of electromagnetism? You might imagine one electron randomly generating a photon that happens to reach another electron. But quantum physics suggests something far stranger, something that challenges our very understanding of how particles interact across vast distances. Quantum physics doesn't work the way we might intuitively think. When a photon is exchanged between two electrons, one electron must send it out, while the other must accept it. But here's the problem. How do they agree on this? Electrons can only communicate through photons, and photons travel at the speed of light. So how can two electrons coordinate something like this when they are separated by vast distances in space? This is where interpretation comes into play. One particular explanation, known as the transactional interpretation, suggests that electrons perform a kind of handshake to exchange photons. But this handshake isn't just a simple back and forth in space, it happens through time itself. One electron sends a signal forward into the future, while the other sends a signal backward into the past. If these signals match, they establish an agreement, allowing the photon to be exchanged. And astonishingly, this process can occur across distances spanning billions or even trillions of light years. However, this idea implies that time travel is an essential part of how the universe works. For many scientists, that's a difficult concept to accept. Some dismiss it as nothing more than a mathematical trick, an artificial workaround that hides a much deeper, unknown truth about reality. So, where does this leave us? As we try to understand the true nature of the universe, we find ourselves on the very edge of scientific understanding, where physics meets philosophy. Is science really about uncovering the ultimate truth, or is it simply the best tool we have to create mathematical models, approximations of a reality we may never fully grasp? Your mind races as you try to process this mind-bending concept, but then a chilling thought takes over everything else. If nothing is truly real, then what are you? Where do your thoughts exist? And, most unsettling of all, where exactly are you? Long ago in ancient Greece, there was a famous story about a ship, the ship of Theseus. This legendary vessel belonged to the hero Theseus, and over the years it endured countless voyages across the sea. But as time passed, the ship started to wear down. The wooden planks rotted, the sails tore, and the nails rusted. To keep it seaworthy, the people of Athens replaced every damaged part with a new one. Slowly, piece by piece, the entire ship was rebuilt. At some point, not a single original part remained, and this raised a profound question. Was it still the same ship? If not, at what exact moment did it stop being Theseus's ship and become something else entirely? Greek philosophers debated this mystery, realizing it wasn't just about a ship, it was about the nature of identity itself. Now, imagine this concept applied to something even more personal: you. Every part of your body is constantly changing. Your blood, for instance, is in a state of continuous renewal. A red blood cell, created deep within your bone marrow, only lives for about 4 months before it is broken down and replaced. Every second, about 5 million red blood cells die, while new ones take their place. In a single year, your body completely replaces its blood 3 times, but it doesn't stop there. Your skin sheds and regenerates every few weeks. Your internal organs, from your liver to your stomach, slowly replace themselves over a period of around 10 years. Even your bones, the sturdy framework of your body, are not permanent. They fully renew about every 15 years. So, if every part of you has been replaced, are you still the same person who was born years ago? If not, when exactly did you become someone new? Unlike the ship of Theseus, this change happens in a gradual, seamless way, making it impossible to pinpoint the moment when the old you became the new you. This question leads us to an even deeper mystery. What makes you, you? For centuries, thinkers have tried to understand the nature of the mind. The ancient Egyptians believed that the heart was the center of thought and the home of the soul. They imagined that emotions, ideas, and memories radiated outward from the heart, controlling the body. Later, the philosopher René Descartes proposed that the mind and the brain were 2 separate things, coexisting and interacting in ways we couldn't fully grasp. Another philosopher, Gottfried Wilhelm Leibniz, tried to illustrate this by asking us to imagine being shrunk down to the size of a flea and traveling inside the brain. He argued that no matter how closely we examined the brain's structure, we would never actually see thoughts, ideas, or emotions within the biological tissue. This led many to believe that the mind was something separate from the brain itself, a distinct entity, perhaps even something beyond the physical world. But in the 20th century, scientific discoveries challenged this idea. Advanced brain mapping technology revealed that thoughts and emotions were not invisible, mystical forces. They were tied to electrical activity in the brain. Researchers discovered that different thoughts, sensations, and emotions lit up specific areas of the brain in measurable ways. Our brains contain an astonishingly complex network of more than 80 billion neurons, each firing signals that spark new signals, creating a constantly changing web of electrical energy. Even with this knowledge, many mysteries remain. Where exactly do thoughts come from? Where do love, creativity, and imagination reside. Despite all our advances, the human mind remains one of the greatest enigmas in science. Even the brain of Albert Einstein, one of history's most brilliant minds, was surprisingly unremarkable in its structure. When scientists examined it, they found nothing that clearly explained his extraordinary intelligence. Some scientists now believe that consciousness is an emergent phenomenon, a property that arises from the immense complexity of the brain's neural connections. This idea of emergence is not limited to human thought. In fact, emergent phenomena are all around us. A famous story from the Soviet era illustrates this concept. In the 1980s, a Soviet official visited London and was puzzled by how the city's bread supply was managed. In the Soviet Union, bread production was strictly controlled by the government, yet inefficiencies often led to long lines at bakeries. The official was amazed to learn that in London there was no central authority organizing bread production, yet somehow everything worked smoothly. The system had emerged naturally from countless individuals working independently. This is similar to an ant colony. If you watch thousands of ants moving around, they seem to act with a shared purpose. But there is no single ant in charge. Instead, complex behavior arises from each ant following simple rules. Nature is full of examples like this. A river, at its core, is just a mass of water molecules interacting through electromagnetism. Yet, from these simple interactions, we get swirling currents, waves, and rapids. Scientists now wonder if even the fundamental forces of the universe, like gravity, might emerge from something even more basic, just as the properties of water emerge from individual molecules. So, could our reality, the rich world of thoughts, emotions, and experiences inside our minds, simply be the result of an incredibly intricate network of neurons firing in patterns? Some find this idea unsettling, as if it strips away the mystery of human existence. But for others, it's a source of wonder, a reminder that within the ordinary workings of biology, something extraordinary emerges, the very essence of what it means to be alive. If consciousness is nothing more than a natural outcome of complexity, just an advanced function of the physical world, then perhaps we could someday recreate it, or even surpass it. This idea has fueled the dreams of artificial intelligence researchers for many decades. Their mission? To build increasingly complex networks, both digital and physical, with the hope that true intelligence will eventually emerge on its own. But there's an even more ambitious branch of science called synthetic intelligence. Unlike traditional artificial intelligence, which focuses on programming computers to mimic human thought, synthetic intelligence takes a different approach. Instead of relying on software alone, physicists are designing intricate networks of microscopic wires, nanowires, that behave like the neurons and connections inside the human brain. These tiny wires can reorganize themselves and, in theory, might develop the ability to store memories. Scientists believe that as electrical currents pulse through these microscopic circuits, they could give rise to something resembling thoughts. At first, this may sound like something straight out of a science fiction novel, but what if we are only a few steps away from creating machines that can think for themselves? Of course, not everyone is convinced. Philosophers who support the ideas of René Descartes, who argued that the mind and body are separate, dismiss this quest as hopeless. They believe that no matter how complex a machine becomes, it will never possess the kind of consciousness that humans do. But others argue that consciousness is just a matter of time and complexity. If that's the case, then one day, these artificial networks could become self-aware. They could wake up. They could truly be alive. But if consciousness is purely physical, then it leads to some unsettling questions. Is your sense of self, the thoughts running through your mind, just the result of electrical signals firing inside the soft tissue of your brain? What if you are nothing more than a brain floating in a vat, hooked up to a system that feeds you a simulated reality? What if you don't even have a physical brain at all, but are instead just a program running on a computer? And what if Descartes was right? What if consciousness does not come from the physical world at all? What if it exists on an entirely different plane of existence, something beyond the grasp of science, a realm where something like a soul might reside? This raises even bigger questions. Why should consciousness be limited to humans? What if it is far more widespread than we assume? What if consciousness exists everywhere? At first, this idea seems too bizarre to consider, but this very concept, known as Pansychism, has been explored by some of history's greatest philosophers. It suggests that consciousness is not unique to humans, but instead is a fundamental part of the universe itself. Every particle, every atom, every speck of dust, every tree, every rock, every star, even the vast galaxies and the black holes that swallow light. What if everything is, in some way, alive? What if even the tiniest building blocks of reality, molecules, protons, quarks, and electrons, have a form of awareness? This notion is too radical for most scientists, but some philosophers argue that it may be connected to the strange mysteries of quantum mechanics. Physicists, however, tend to reject the idea outright. They see it as a step too far, a concept that stretches beyond the boundaries of what they consider real science. And so, as is often the case, the two groups continue to debate, rarely finding common ground. But could it be true? Could the universe itself be conscious? Your scientific mind ponders this for a moment before dismissing it as an idea too vast, too strange, too impossible, and then your gaze drifts toward an apple sitting nearby. You focus on it, taking in its color, its texture, its shape. Your mind processes everything you've just contemplated, the nature of existence, the mystery of consciousness, the unsettling possibilities of reality. Imagine a scientist. What picture comes to mind? For many, it's Albert Einstein, with his wild, unkempt hair, deep wrinkles, and perhaps even that famous image of him sticking out his tongue. Others might picture Isaac Newton, dressed in the formal attire of the 1700s, complete with a powdered wig. But here's the thing. These images capture these great minds in their later years, long after they had made their most groundbreaking discoveries. Science, in many ways, is a young person's pursuit. The popular television show, The Big Bang Theory, may have exaggerated the quirks of scientists for comedic effect, but there's some truth to the idea that many great scientific breakthroughs come from young minds. Take Einstein, for example. He was just 26 years old during what is now called his miracle year, a time when he produced some of the most revolutionary ideas in physics. Isaac Newton, too, was incredibly young when he had his most profound insights into the nature of the universe. In the year 1666, at the age of just 23, Newton had already shown himself to be a prodigy, studying at the University of Cambridge. But 1666 was no ordinary year. The dreaded Black Death had returned to Britain, a horrific plague that had first devastated Europe in the 14th century. Although centuries had passed, the disease never truly disappeared, periodically resurfacing to claim more lives. As the plague swept through the cities, people fled to the countryside, seeking safety from the deadly outbreak. Among them was young Newton, who left Cambridge and returned to his family home in the village of Woolsthorpe in Lincolnshire. While death cast its shadow over the land, Newton found solace beneath the branches of his now legendary apple tree. It was there, in solitude, that his mind wandered into the mysteries of the universe. Newton's work on motion and time led him to divide time into three distinct categories: the past, which had already happened, the future, which had yet to come, and the present, the fleeting moment of now. According to his equations, reality existed in this precise moment, moving forward from the past and shaping the future in a predictable way. His laws were deterministic, meaning that if someone had perfect knowledge of an object's current state, they could calculate its exact position and condition at any other point in time, whether in the past or the future. But this raised a mind-boggling question. If we can predict the future with absolute certainty, is it truly unknown? Has the past really disappeared? In a Newtonian universe, the past, present, and future all seem to exist together in a grand, unchanging structure, while we merely experience reality, one moment at a time. This concept made a dramatic return centuries later with Einstein's theory of relativity. Instead of time and space being just a backdrop, Einstein made them central to the story. Every particle in the universe traces a unique path, its world line, through 4 dimensions, including time. And just like Newton's universe, Einstein's was also deterministic, meaning that every moment, past, present, and future, already exists. This idea became known as the block universe. In this view, time is not something that moves forward like a river. Instead, the entire history of the universe is already laid out, like a vast, unchanging block. We simply experience one moment at a time as we move along our own world lines. The equations of relativity make it clear. There is nothing inherently special about now. The future is not a mystery. It is just another part of an already existing reality. In Albert Einstein's version of the universe, there exists a fascinating yet unsettling concept known as the block universe, a model of reality that challenges everything we assume about free will and the passage of time. At first glance, the ability to make choices, to decide between different possible futures, seems like an inseparable part of being human. But in the block universe, this sense of freedom is nothing more than an illusion. According to this theory, the past, present, and future are all set in stone, already existing as part of a vast, unchanging cosmic structure. The future is not something that unfolds moment by moment. It is already written, just as the past is unchangeable. This idea has consequences far beyond philosophy. It stretches into the realm of science fiction and raises incredible possibilities. If both the past and future are already out there, could we somehow visit them? Could ancient creatures like the dinosaurs still exist somewhere along the timeline, just beyond our reach? Could future civilizations that have yet to be born already have a place within the fabric of time? Some physicists speculate that there might be hidden pathways in space-time, twisting and intricate routes through the cosmos that might allow us to experience these different moments in our present. Yet, despite its logical foundation, the block universe feels deeply unnatural. We experience time as something that flows, not as a frozen landscape where every event is already determined. The future should be unknown, something yet to be created, not something pre-written. This discomfort led many scientists to search for alternatives, theories that could make sense of reality in a way that better aligns with human intuition. This is where quantum mechanics enters the picture. Unlike Einstein's classical universe, quantum mechanics introduces probabilities instead of certainties. It suggests that the future isn't rigidly defined, but instead emerges from a sea of possibilities. In this view, the universe behaves like a block universe up to a point, that point being right now. The present moment is constantly being built, piece by piece, as quantum processes resolve themselves into definite outcomes. Think of reality as a vast, ever-growing tapestry. The past is woven tightly into the fabric, set in stone, while the present is the active edge of the loom, where new threads are constantly being added. The future, however, remains unformed, waiting to be stitched into existence. This idea aligns with a theory known as loop quantum gravity, one of the leading candidates for the elusive theory of everything. In this framework, space and time are not continuous, but are instead composed of tiny, fundamental loops that knit reality together. The now is where these loops are being actively woven, while the past is the completed fabric behind us. This perspective leads to mind-bending questions. Take something as simple as an apple sitting on your table. The apple you see right now, is it really the same apple you saw just a moment ago? Or is its very essence being rebuilt at every instant? Are you, yourself, constantly being recreated moment after moment as the universe assembles reality on the fly? The deeper you explore these questions, the more unsettling they become. Reality itself starts to feel unstable, as if it could dissolve under your fingertips. And so, a simpler, yet more profound question arises. What is reality? Perhaps the block universe is correct, and time is nothing more than a frozen landscape, giving us only the illusion of free will. Or maybe loop quantum gravity is right, and the universe is being built piece by piece, one quantum event at a time. But what if the truth runs even deeper? What if reality is not physical at all? This idea, as strange as it sounds, has gained traction among physicists and philosophers alike. At its core, the universe operates on information, on patterns, numbers, and calculations. Every law of physics, from Newton's equations to Einstein's relativity, is ultimately a set of rules for processing information. Consider a simple example. If you know the location and speed of a ball flying through the air, the laws of physics allow you to predict where it will land. These laws take the information about the present and process it into predictions about the future. This concept is even more striking in quantum mechanics, where the state of a system is encoded in a mathematical entity known as the wave function. As time progresses, the wave function evolves, following the rules of quantum physics, constantly transforming information into new information. By the middle of the 20th century, scientists discovered a profound link between information and energy. The mere act of processing information requires energy, whether it's a computer flipping a digital switch from 1 to 0 or your brain processing a thought. This realization led to an astonishing hypothesis. What if everything in the universe, including our thoughts, experiences, and even the fabric of space-time, is nothing more than information being processed? This radical idea forms the foundation of what is known as the simulation hypothesis. According to this perspective, all of existence is simply a vast computation, with reality itself being nothing more than an elaborate processing system. This goes even further than the classic brain in a vat thought experiment, because in this scenario, there would be no physical brain at all. Reality, as we perceive it, would be nothing more than numbers, information, and patterns unfolding in some incomprehensible underlying system. The idea that we might be living in a simulation immediately leads to a big question. Where exactly is this simulated world being processed? Could it exist in a higher level of reality, a place beyond anything we could ever understand? And if so, why was our world created in the first place? What if we are nothing more than characters in an incredibly advanced version of a video game, like The Sims? But what if the simulation wasn't even made for us? What if it was built for an entirely different reason? Perhaps to study artificial worlds, and we just happen to emerge as a side effect? What if the creators of this simulation have no idea that we exist, and even if they did, they wouldn't care? These are the kinds of questions that can drive endless debates. Maybe we'll never know the answers. But here on Earth, scientists already create artificial universes, computer-generated models designed to help us understand our own reality. They even experiment with different versions of the universe, where the laws of physics are completely different from what we know. If technology keeps advancing, could we one day create digital beings who are fully conscious, living inside a synthetic world of our own making? But even if our reality is just a simulation, wouldn't that mean our creators exist in a real world? A world that is actually physical? Or have we just moved the mystery to another level? Is it like the old idea that the Earth rests on a giant turtle, which itself stands on another turtle, and so on, with no end? We often imagine that for a simulation to exist, there must be a supercomputer somewhere running all the calculations that create our universe. But what if there is no physical computer? What if reality itself has no physical foundation? What if everything we see, feel, and experience is just math, nothing more than an endless stream of calculations? This is the mind-bending idea behind the mathematical universe theory, proposed by Swedish-born physicist Max Tegmark. At first, Tegmark was focused on the mysteries of cosmology, the study of the universe and its origins. But eventually, he turned to one of the biggest questions of all. What if everything, including space, time, and even consciousness, is just math? Unlike the simulation hypothesis, which assumes there is a computer running our reality, Tegmark's idea suggests that mathematics itself is the only thing that truly exists, without any need for a machine to process it. But if that's the case, where do these calculations take place? And what is doing the calculating? We usually think that to compute something, you need a computer. But if math is the most fundamental thing in existence, then it simply exists on its own. It doesn't need a location or an explanation. Tegmark's mathematical universe isn't just about our reality. It includes every possible universe that could exist, each one following different sets of mathematical rules. Within this infinite collection of worlds, some universes might look almost exactly like ours, with countless versions of you living slightly different lives. But there would also be universes completely alien to us, where the fundamental forces of nature are different, or where space and time don't work the way we expect. The number of possible mathematical realities is so enormous that it might be endless, far larger than the small fraction of math we use to describe our own universe. And now, for the strangest and most unsettling possibility of all. In an infinite mathematical universe, the right combination of calculations could randomly come together to create something that looks exactly like your mind, complete with all your memories and thoughts. For an instant, you would exist, experiencing a reality that feels just as real as this one. You might even be thinking about something as simple as picking an apple from a tree. To this newly formed mind, everything would seem normal. You would remember your past, your childhood, and all the events of your life. But in truth, your existence would be nothing more than a brief mathematical fluctuation, a momentary blip in the vast ocean of numbers. And just as suddenly as you appeared, you would vanish, erased by the endless flow of calculations. This means that, statistically speaking, these fleeting minds, called Boltzmann brains, should be far more common than entire universes like ours. So, how do you know that you aren't just one of these temporary minds, about to disappear in an instant? How do you know that the world around you wasn't just created a moment ago, complete with all your memories? And even more unsettling, how do you know you won't simply cease to exist in the next moment? Sadly, even if we try to remove the idea that the universe is based on mathematics, it doesn't solve the real problem. Scientists believe that our universe has an endless amount of time ahead of it. And in this infinite future, the universe will become cold and lifeless. Long after the last star burns out and the final black hole disappears into nothingness, space will be left dark and empty. At first glance, it might seem like this is the final chapter of the universe's story, an eternal void where nothing new ever happens. It sounds like the future cosmos will be a silent, uneventful place. But is that really the case? Could the universe still hold surprises even after all the stars are gone? To answer this, we need to take a closer look at one of the most misunderstood ideas in physics: entropy. Back in the 19th century, a brilliant scientist named Ludwig Boltzmann had some revolutionary ideas. Before most people accepted it, he strongly believed in the atomic theory, the idea that everything is made up of tiny, indivisible particles called atoms. He also reinterpreted the laws of thermodynamics, the rules that govern how energy flows and changes, in terms of how these atoms move and interact. Many of the top scientists of his time criticized his views, but just before his death in the year 1906, new scientific evidence finally proved that atoms were real. Boltzmann spent a lot of time thinking about how atoms are arranged. Imagine the air around you. It's made of countless molecules of nitrogen, oxygen, and carbon, all moving chaotically, colliding with each other and with everything around them. Each specific arrangement of these molecules looks almost identical to another, but we all know from experience that air doesn't just randomly gather into one corner of a room. On the other hand, If we did start with all the air molecules packed into one corner, they would quickly spread out and fill the entire space. Boltzmann discovered that this behavior is not random. It follows a predictable pattern based on probability. He showed that highly specific arrangements of atoms naturally evolve into more general, scattered arrangements over time. This process is known as the increase of entropy. In simple terms, entropy is a measure of disorder, and it follows one of the most unbreakable rules in the universe. Things tend to move from order to chaos. To understand this better, let's talk about energy. The total amount of energy in a system always stays the same. That's another fundamental law of physics. But not all energy is useful. Some of it can be harnessed to do work, while some is just wasted. As entropy increases, useful energy is slowly turned into useless energy. Imagine you have a sealed container filled with compressed air. This is similar to the situation where all the air in a room is squeezed into one corner. In this state, the system has low entropy because the energy inside is highly concentrated and can be used for something useful. If you open a valve, the high-pressure air will rush out, and this escaping air can spin a wheel. That spinning wheel could then be used to generate electricity or perform mechanical work. But once the air pressure inside the container has balanced out with the surrounding air, everything stops. The wheel no longer spins, and no more useful energy can be extracted. This is true for every physical process. Whenever energy is used, some of it is lost in a way that can never be recovered. Even your own body constantly fights against entropy. To stay alive, you need a steady supply of concentrated energy, which you get from food. But as your body processes food, it releases waste and heat, both of which are forms of energy that can no longer be used efficiently. In this way, every living being is unknowingly contributing to the slow increase of entropy across the universe. Entropy has been rising ever since the beginning of time, with useful energy gradually disappearing. But this raises a deep and puzzling question. Why did the universe start out with such incredibly low entropy, meaning so much useful energy? Scientists still don't have a clear answer. Imagine a universe where there is no energy left to do anything useful, an endless expanse of darkness and stillness. According to the laws of thermodynamics, first explained by a scientist named Ludwig Boltzmann, this is the ultimate fate of the cosmos. But here's where things get interesting. These laws are based on statistics, meaning that while certain things seem impossible, they could still happen given enough time. Think about the air in your room suddenly gathering in just one corner, leaving the rest of the space empty. Or imagine a game of billiards where the balls, after scattering across the table, somehow roll back into their perfect starting positions. Incredibly unlikely, right? But Boltzmann said that if we wait long enough, far longer than the current age of the universe, these bizarre events must eventually happen. And if there's one thing the universe of the distant future will have plenty of, it's time. Even in a universe that has become completely disordered, tiny moments of order will occasionally appear. The laws of physics, specifically thermodynamics and quantum mechanics, allow for fluctuations, brief, random changes in the state of the universe. Most of the time, these fluctuations will create tiny, short-lived particles that vanish almost as soon as they appear. But on extremely rare occasions, much more complex things could pop into existence. Once in a great while, something as intricate as a human mind could spontaneously emerge. These fleeting minds, called Boltzmann brains, would usually be empty, blank slates with no thoughts or memories, disappearing in an instant. But every now and then, a Boltzmann brain might form with a full set of memories, believing it has lived an entire life, even though it only just came into being. Here's where things get truly mind-bending. With an infinite amount of time, these conscious minds wouldn't just appear once, they would appear again and again, an endless number of times. In fact, your exact consciousness, every thought, every memory, every experience you have right now could emerge repeatedly throughout eternity. Statistically speaking, this means that you are far more likely to be a Boltzmann brain, momentarily existing in the cold, empty void of the universe, than a physical human sitting here, enjoying something as simple as a ripe, juicy apple. So, how can you be sure that you haven't just popped into existence this very moment? How can you be certain that in an instant you won't simply vanish? For now, at least, you are still here. And as your thoughts swirl through the nature of reality, your eyes settle on a single apple, the apple that started you on this philosophical journey. You recall everything you've pondered, the ideas of ancient thinkers like Plato, the strange and unpredictable world of quantum physics, the concept of a universe where time is an illusion, and the possibility that reality itself might be a hologram. Have you ever wondered just how much computers have advanced since the early days? Let's take a guess. Have their capabilities increased hundreds of times? Maybe thousands? Well, the real answer is mind-blowing. Since the 1940s, computers have become hundreds of trillions of times more powerful, and that's not even the end of it. Experts predict that in the next few decades, their power could grow millions of times more. Now, why does this matter? Because this kind of computing power could allow us to create virtual worlds so advanced that the characters inside them wouldn't just follow pre-programmed instructions. They could be as complex as us, with thoughts, emotions, and even consciousness. But here's the unsettling part. They wouldn't know they were inside a simulation. That raises a chilling question. What if we are those very characters? Sounds ridiculous, right? But is it really? Some of the brightest minds in the world take this idea seriously. Elon Musk, for example, has publicly stated that there's a 1 in a billion chance that we're living in base reality, meaning the real, non-simulated world. And he's not alone. More and more scientists and philosophers are coming to the same conclusion. To understand the first piece of evidence, we need to think about how computer simulations and virtual worlds function. Imagine you're playing a video game. As you move your character forward, the game only renders what's directly in front of you: streets, buildings, people. Everything behind you doesn't exist until you turn around. Now, let's take it a step further. Think about wearing a virtual reality headset. When you look straight ahead, the world around you appears normal, but nothing behind you is loaded into existence until you turn your head. The moment you do, the headset system generates the scene in real time, while what was in front of you disappears. But here's the eerie part. How do we know something exists when we're not looking at it? What if the universe only renders things when we observe them? This brings us to one of the strangest discoveries in physics, the observer effect. You might have heard of the double-slit experiment, also known as Young's experiment. This is one of the most famous physics experiments ever conducted, and it's been repeated countless times with mind-boggling results. Here's what happens in simple terms. When scientists send light through 2 slits in a screen, it behaves like a wave, spreading out in all directions. But the moment they measure which slit the light goes through, something bizarre happens. The light stops behaving like a wave and acts like individual particles instead. In other words, when unobserved, light behaves one way. But the moment someone watches it closely, it changes its behavior. That might not sound too strange at first, but think about it this way. Imagine you have a cup of coffee. You look at it, and it's just a cup of coffee. But the second you look away, it transforms into the sound of ocean waves. Sounds impossible, right? Yet this is exactly what happens at the quantum level. Scientists have observed the same behavior in electrons and atoms, the very building blocks of everything we see and touch. Imagine a world where certain rules govern everything, rules that cannot be broken under any circumstance. One of the most intriguing and unchangeable rules of our universe is the speed of light. No matter what we do, we can never go faster than this ultimate speed limit. It is a fundamental law of physics that nothing can exceed approximately 300,000 kilometers per second. At first glance, this might seem unfair. Why should there be such a limit? If we want to explore distant galaxies, Why must we be bound by this unyielding restriction? It almost feels as if we are trapped inside some kind of programmed reality. But what if we looked at this from a different angle? Think about your smartphone or computer. Every device has a processor that operates at a fixed speed, measured in gigahertz. No matter how advanced the processor is, it has a maximum speed it cannot surpass. We accept this limitation without question because we understand that the hardware is designed this way. But when it comes to the speed of light, many people find it frustrating. Now, what if the limit of the speed of light is not a natural restriction, but a feature of a much larger system, perhaps a vast, simulated reality? If our world were part of an incredibly sophisticated simulation, then the speed of light could simply represent the maximum processing speed of that system. The more we study the universe, the stranger it seems. Scientists have proven that as an object moves faster, time slows down for it. This phenomenon, called time dilation, has been confirmed through many experiments. If you were on a spaceship that could travel at the speed of light, something astonishing would happen. Imagine you set off on a journey to a galaxy 3 billion light-years away. From your perspective, you would arrive there instantly. However, for people on Earth, 3 billion years would have passed. For light particles, called photons, time completely stops. A photon traveling from a distant star may have taken billions of years to reach Earth, but from the photon's perspective, no time has passed at all. This means that faster-than-light travel is impossible because time cannot slow down further than zero. But why does speed affect time? Why are space and time so deeply connected? It seems like a bizarre rule to exist in a physical universe, but it makes perfect sense in a digital one. If our reality were a simulation, then the speed of light could be a built-in limit of the system, just like a processor has a fixed clock speed. Here's another clue that suggests our reality might be more like a computer program than we think. The universe appears to be pixelated. In modern physics, there is something called the Planck length, which is the smallest possible measurement of space. It is about 1.6 times 10 to the power of negative 35 meters. Nothing in the universe can be smaller than this. It's as if space itself is made up of tiny, indivisible units, just like pixels on a screen. Not only that, but time also has a smallest possible unit, called Planck time, which is about 5.4 times 10 to the power of negative 44 seconds. This means that the universe doesn't flow continuously like a river, but instead operates in tiny, rapid flashes, like frames in a video game. If you look at a digital screen up close, you'll see that the image is made up of tiny squares, or pixels. Similarly, the universe might be made up of tiny space pixels that form everything we see. But the similarities don't end there. A computer screen refreshes at a specific rate, usually 60 times per second. If the universe is a simulation, then it might also refresh, but at an unbelievably fast rate, trillions and trillions of times per second. We don't notice it because it happens far beyond human perception, just like we don't notice the flicker of a high-speed monitor. This idea raises an incredible possibility. What if reality itself blinks in and out of existence, just like a digital display? One of the strangest mysteries in physics is quantum entanglement. This occurs when two particles become linked in such a way that changing one particle instantly changes the other, even if they are on opposite sides of the universe. To understand this, imagine you have a pair of gloves. One glove is right-handed and the other is left-handed. If you send one glove to Mars and keep the other on Earth, the moment you look at the glove on Earth and see that it's right-handed, you immediately know the one on Mars is left-handed. But here's where it gets strange. With quantum entanglement, the particles don't decide their properties until someone observes them. If you check one particle and find that it is spinning in a certain direction, the other particle, no matter how far away, instantly assumes the opposite spin. This happens faster than the speed of light, which seems to break the very rules of physics. Albert Einstein called this phenomenon spooky action at a distance because it seemed impossible. However, experiments have repeatedly confirmed that quantum entanglement is real. If our universe were a giant computer simulation, this instant connection between entangled particles might be similar to how data is stored and retrieved in a digital system. In a video game, two characters can be connected by code, no matter how far apart they appear to be on the screen. Could quantum entanglement be a sign that we are living in a world where everything is connected by some hidden computational framework? Another fascinating detail is that physicists often describe the speed of light not just as a speed limit, but as the fastest rate at which information can be transmitted. In other words, the universe behaves like a giant information processing system. In a computer simulation, data can only be processed at a certain speed. If our reality were a digital construct, then the speed of light might simply represent the maximum data transfer rate of the system. This idea might sound like science fiction, but many scientists take it seriously. Some researchers have even suggested experiments to test whether the universe has a fundamental resolution, just like a computer screen. If they find that space and time are made up of tiny, indivisible units, it would be strong evidence that our reality is not continuous but digital in nature. If everything we've discussed is true, it would mean that the universe is not an endless natural expanse, but a programmed environment running on an unimaginably powerful computational system. The speed of light, the pixel-like nature of space, time's strange relationship with motion, and the bizarre behavior of quantum entanglement all hint at a reality that behaves more like a high-tech simulation than a purely physical world. Scientists initially believed that entangled photons might already contain information about their spin before being measured. However, experiments inspired by Thomas Young's famous double-slit experiment, repeated and scrutinized countless times during Albert Einstein's era, revealed a surprising contradiction. These tests consistently showed that entangled photons had no predetermined spin. Instead, their spin only appeared at the moment of measurement, as if they decided their state only when observed. This seemed to support Einstein's skepticism about quantum mechanics, suggesting that something was fundamentally flawed in the theory. However, 17 years after Einstein's death, a physicist named John Bell challenged this idea with an incredibly clever and complex experiment. His goal was to test whether elementary particles truly carried hidden information about their spin before being measured. The results were astonishing. Bell's experiment demonstrated, with absolute clarity, that particles did not have a defined spin before measurement. Instead, they only acquired a spin the moment they were observed. In other words, before being measured, photons had no spin at all. They simply existed in a state of uncertainty. This shattered classical ideas and proved that the common comparison between quantum entanglement and pairs of gloves, where one glove is predetermined to be left-handed and the other right-handed, was completely inaccurate. What made this even more mind-blowing was that entangled particles seemed to communicate their state to each other instantly, at speeds far beyond what classical physics deemed possible. If two entangled photons were separated to opposite sides of the universe and one was measured to have an up spin, the other would immediately assume a down spin. This instantaneous reaction left physicists completely baffled. How could information travel faster than the speed of light? In the year 2008, a team of Swiss scientists from the University of Geneva set out to measure the speed of this mysterious quantum communication. They sent two entangled photons to locations 11 miles, 18 kilometers, apart. When they measured one of them, they closely monitored how quickly the second photon reacted to the change. Their equipment was sensitive enough to detect even the tiniest delay, down to speeds 100,000 times faster than light. But they found no delay at all. This suggested that quantum entanglement might not just be faster than light, it might be instantaneous. Einstein once famously argued that nothing in the physical universe could communicate instantaneously. But what if he was only wrong about the physical universe itself? What if our reality isn't purely physical, but more like a vast digital simulation? If we think of photons like pixels on a screen, the explanation becomes simpler. Imagine that two pixel-like photons become entangled through a shared program. If one pixel is assigned an up spin and the other a down spin, their program ensures they remain opposites, no matter how far apart they appear on the screen. When one photon is measured, its program selects a spin randomly, and the second photon's program instantly assigns it the opposite spin. In this scenario, distance is meaningless because the processor controlling the simulation doesn't need to physically move information. It simply updates the program's state. And if we truly are living in a computer-generated universe, this could also explain one of the biggest mysteries in science, the Fermi paradox. The paradox asks, if intelligent alien life should be common in the universe, why haven't we found any evidence of it? Perhaps the reason is shockingly simple. Maybe extraterrestrial civilizations just aren't programmed into our simulation. If that's the case, the moment we encounter alien life might not be determined by chance or science, but by the decisions of the universe's game designers. After all, in a simulation, new elements can be introduced at any time. There's a strange and puzzling phenomenon that has left many people questioning their own memories, and in some cases, even reality itself. This phenomenon doesn't belong to the world of physics or science fiction. It exists in society, in the way people collectively remember events, brands, and historical facts. It all began in the year 2009 when a woman named Fiona Broome, who calls herself a paranormal researcher, stumbled upon something shocking. For as long as she could remember, Fiona Broome had been absolutely certain that Nelson Mandela, the famous human rights activist and former president of South Africa, had died in prison during the 1980s. She was so convinced of this that she could recall news reports, newspaper headlines, and even public mourning over his death. But to her surprise, she discovered that Nelson Mandela had actually been released from prison in the year 1990 and had even served as the president of South Africa for several years, before passing away in the year 2013. At first, this might sound like a simple case of one person misremembering something. However, what made it extraordinary was that Fiona Broome wasn't the only one who had this memory. When she started asking other people about it, she realized that many others also believed that Nelson Mandela had died decades before his actual passing. Some even claimed to remember watching his funeral on television and hearing his daughter deliver an emotional speech. The fact that so many unrelated people shared the same false memory led Fiona Broome to investigate further. The results of her research were astonishing. There were thousands of people across the world who remembered the exact same incorrect details. When Nelson Mandela actually died in the year 2013, these people were completely shocked. They felt as though history had somehow changed, or that they had been transported into an alternate reality where things were not as they remembered them. Fiona Broome gave this strange phenomenon a name: the Mandela effect. But as intriguing as this was, it was only the beginning. With the rise of the internet and social media, it quickly became clear that this phenomenon wasn't limited to just one historical event. Thousands of people from different countries and cultures began sharing their own experiences of memories that didn't match up with reality. Some of the most famous examples include the Volkswagen logo mystery. The logo of the famous German car manufacturer Volkswagen has a very specific design, with a small gap between the V and the W. However, thousands of people remember the logo differently, without the gap. The Monopoly man's missing monocle. Many people remember the famous mascot of the board game Monopoly, a man in a top hat wearing a monocle. But in reality, he never had one. This has left countless people confused as they vividly recall an image that never existed. The peanut butter that was never called Jiffy. Many people swear that there used to be a brand of peanut butter called Jiffy. However, the brand has always been called Jif. It seems that people are merging the names of Jif and another peanut butter brand, Skippy, in their minds. Pikachu's tail, black tip, or not. The famous Pokémon character Pikachu is remembered by many as having a black tip at the end of his tail. However, his tail has always been completely yellow. C-3PO's silver leg. In the Star Wars movies, the robot C-3PO is widely thought to be entirely gold, but in reality, he has always had one silver-colored leg. Even hardcore Star Wars fans get this detail wrong. These are just a few examples, but there are many more. What makes the Mandela effect so mysterious is that it's not just about individual people misremembering things, it's about large groups of people all sharing the exact same incorrect memory. Because so many people experience the Mandela effect, some researchers and theorists have tried to find an explanation. One of the more mind-boggling theories suggests that these memory inconsistencies might be glitches in our reality, as if we were living inside a simulated world similar to a massive video game. This idea is linked to something called the simulation hypothesis, which suggests that our entire universe might actually be an advanced computer simulation created by a higher intelligence. This might sound like science fiction, but it's a concept that serious scientists and philosophers have considered for years. To understand why some experts believe in the possibility of a simulated reality, let's look at the rapid advancement of computer technology. In the 1940s, the world's first true programmable computer, called ENIAC, could perform about 5,000 calculations per second. That was considered groundbreaking at the time. But today, the most powerful supercomputer, called Frontier HPE Cray EX 235, can perform 1 quintillion calculations per second. To put that into perspective, today's fastest computer is 200 trillion times more powerful than the first one, and this has happened in less than 100 years. If computing power keeps increasing at this rate, it's not hard to imagine that in the future, humans, or some other advanced civilization, could create computer simulations so realistic that they would be indistinguishable from reality. A respected philosopher named Nick Bostrom, a professor at Oxford University, published a groundbreaking paper in the year 2003 called The Simulation Argument. In this work, he proposed that if certain conditions are true, then it is highly likely that we are living in a simulated world rather than a real one. One of the key points of his argument is about consciousness, the ability to think, feel, and be self-aware. If humans could one day create a simulation advanced enough to include people with artificial consciousness, those people inside the simulation would never know that they were not real. Think about modern video games. Characters in these games follow rules programmed by developers. But what if, in the future, those characters became so advanced that they could think for themselves? If that were to happen, how would they know that their world wasn't real? Bostrom's theory suggests that it is entirely possible that our own reality is just a highly advanced simulation, created by beings far more intelligent than us. If true, then the Mandela effect could be one of the signs of small glitches or changes in this programmed reality. Over the past 80 years, computing power has increased by an almost unimaginable amount, 200 trillion times. But what if progress keeps going at this pace for another 80 years, or even 80,000, or 80 million? That brings us right to Nick Bostrom's second assumption, that technological progress will not slow down anytime soon. For a long time, people assumed that humanity would continue advancing without hitting an obstacle that couldn't be overcome. But in recent years, some experts started to worry. A major challenge seemed to be appearing on the horizon, making futurologists question whether progress could continue at the same speed. You may have heard of Moore's law. If not, here's a quick summary. It's not really a law, but an observation made by Gordon Moore, one of Intel's founders. He noticed that computer power tended to double about every 2 years, and for decades that prediction held true with only small variations. But then, something changed. The rapid increase in computing power started slowing down. By the early 2000s, scientists noticed that making computer chips more powerful was becoming harder. Transistors, the tiny components that make computers work, could only be made so small before running into physical limitations. Signal transmission, heat production, and energy consumption all became serious challenges. As a result, creating more powerful processors became not only incredibly complex, but also extremely expensive. This led some experts to worry that we had reached the limits of what was possible. However, the tech industry didn't give up. Instead of trying to keep making processors faster in the same way, companies explored new solutions. They introduced multi-core processors, improved algorithms, and designed specialized hardware for specific tasks. And now, we stand at a groundbreaking moment. Quantum computers are no longer just an idea. They are becoming a reality. Quantum computing isn't just about more powerful machines. It represents a completely different way of processing information. The physics behind it operates on an entirely different level. And if quantum computers become widely available and affordable, they could lead to breakthroughs beyond anything we can currently imagine. Looking ahead, if quantum computing becomes as common as regular computers are today, who knows what else humanity might create? This is why Bostrom's assumption that computing power will not decline seems to make perfect sense. But here's the bigger question. What if none of this matters? What if we don't even make it far enough to see these incredible technologies develop? There's always the possibility that humanity could destroy itself before reaching its full potential. A nuclear war, an asteroid impact, or some other catastrophe could wipe us out before we become an interplanetary species. However, if we can establish human colonies on other planets, our civilization has a real chance of surviving indefinitely. That's exactly what Elon Musk is trying to achieve with his Mars mission. He wants to make sure humanity has a backup plan, and he's already made significant progress toward that goal. Now, here's where things get even more interesting. Bostrom's fourth assumption suggests that highly advanced civilizations might have a reason to create simulations, possibly even simulations of their own past. Imagine if, instead of reading history books, an advanced civilization could experience what life was like for their ancestors by running detailed simulations. Or perhaps they do it for entertainment, like an incredibly advanced version of a video game. And here's the mind-bending question. What if we are already inside one of these simulations? If a civilization far more advanced than ours had the ability to create such a realistic simulation, we might not even realize we were part of it. Imagine this. If there are countless simulated worlds, the odds that we're living in the original, real world are pretty slim. It's much more likely that we're inside one of those simulations. That's the idea behind the simulation hypothesis, and it has some of the greatest minds in science seriously considering the possibility. Renowned astrophysicist Neil deGrasse Tyson explains it like this. If we can accept that it's possible to create a simulation within a simulation, then the likelihood that we're in one of these artificial realities skyrockets. Think about it. Even with today's technology, we can already create immersive virtual worlds. Now, fast forward to a future where technology is far more advanced. Imagine a world where we can generate entire digital universes, complete with characters who believe they have free will. Now, picture yourself as one of those characters. You think you're making your own choices, but what if everything you experience is just a part of the simulation? Now, let's say you invent a computer inside that simulation. Using that computer, you create yet another simulated world. This process repeats endlessly, creating layer upon layer of virtual realities. If you randomly threw a dart at this collection of universes, would you be more likely to hit the one real world at the beginning of it all, or one of the countless simulations that came after? The odds overwhelmingly favor the latter. Tech billionaire Elon Musk takes this theory even further. He argues that we should hope we're living in a simulation. According to Musk, civilizations either develop technology capable of creating hyper-realistic simulations, or they eventually go extinct. He believes it's far more likely that we are part of a simulation rather than existing in a raw, original reality. Philosopher Nick Bostrom, who originally formulated the simulation hypothesis, also suggests that the chances we're in a simulation are incredibly high. His argument is based on probability. If advanced civilizations are capable of creating countless simulated realities, then statistically, the odds that we're in the one true reality are close to zero. Neil deGrasse Tyson has refined his position over time. He now suggests that if humanity hasn't yet developed the ability to create hyper-realistic simulations, then we're either in the base reality, the original universe, or in the last simulation at the end of a long chain. That would mean we have a 50-50 chance of being real or simulated. The difficulty in proving or disproving the simulation theory was highlighted by philosopher David Chalmers. He pointed out a major problem. If we are in a simulation, then the creators of that simulation could easily manipulate any evidence we find. In other words, even if we try to test our reality, the results could be programmed to mislead us. Quantum superposition is one of the most fascinating ideas in quantum mechanics. At its core, this principle suggests that a quantum system can exist in multiple states at the same time, rather than being confined to just one. This strange behavior comes from the fact that the fundamental equation governing quantum mechanics, known as the Schrödinger equation, is what mathematicians call a linear differential equation. In simple terms, this means that if you take two different solutions to this equation and mix them together, the result is also a valid solution. To understand this better, imagine a quantum system, let's say an electron. The state of this electron is determined by a special mathematical function, which is essentially a wave that describes its behavior. According to quantum mechanics, this wave function is not just a single wave, but rather a blend of many different waves, each representing a possible state the electron can be in. This blending of states is called superposition. Now, let's go a little deeper. The wave equation that describes a quantum system has to be both linear and homogeneous, which means that if you have two different valid solutions, let's call them psi1 and psi2, you can combine them in any way you want, using different weightings or coefficients, and still get another valid solution. But the weirdness of superposition doesn't stop there. A quantum wave function can be described in two different ways, either in terms of position, where the particle is, or in terms of momentum, how fast and in what direction it is moving. These two descriptions are not separate, but connected by something called a Fourier transformation. This transformation is itself a kind of quantum superposition, meaning that every possible position can be described as a mix of different momenta and vice versa. Now, when scientists perform measurements on quantum systems, they often express the system as a mix of special mathematical objects called eigenvectors. Each eigenvector represents a possible outcome of the measurement, and the superposition of these eigenvectors determines the probability of each possible result. The concept of superposition is not just theoretical. It plays a crucial role in the real-world development of quantum computers. In a regular computer, information is stored in tiny units called bits, which can be either 0 or 1. But in a quantum computer, the fundamental unit of information is called a qubit, which can exist in a superposition of both 0 and 1 at the same time. This allows quantum computers to process multiple possibilities simultaneously, making them incredibly powerful for certain types of calculations. However, controlling these qubits is one of the biggest challenges in quantum computing. Some quantum systems, like nuclear spins, are very stable and resistant to outside disturbances, but at the same time, their stability makes them harder to manipulate and read. Scientists are still working on ways to harness quantum superposition effectively, which could one day revolutionize technology and computing as we know it. Quantum entanglement is a strange and fascinating phenomenon where tiny particles, like photons or electrons, become so deeply connected that their properties are linked no matter how far apart they are. Even if they are separated by a vast distance, millions or even billions of miles, their connection remains instant. This means that if something happens to one particle, the other instantly knows about it. even though no signal has traveled between them. This idea is at the core of what makes quantum physics so different from classical physics. In classical physics, objects behave in predictable ways based on direct cause and effect. But in the quantum world, things don't work that way. Quantum entanglement is a key feature of quantum mechanics and has no equivalent in classical mechanics. One of the most fascinating aspects of entanglement is that measurements of certain properties, like spin, polarization, or momentum, are always perfectly connected. Imagine two entangled particles with a total spin of 0. If one particle is measured and found to spin clockwise, the other will always spin counterclockwise, even if it's on the other side of the universe. This happens instantly, defying our usual understanding of time and space. This bizarre behavior led to heated debates among some of history's greatest scientists. In the year 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a famous paper outlining what is now called the EPR paradox. They argued that quantum mechanics must be incomplete because it seemed to allow information to travel faster than the speed of light, something Einstein considered impossible. He famously called it spooky action at a distance, believing that there must be hidden variables, unknown factors within the particles themselves that would eventually explain this mystery. However, later experiments proved that there are no such hidden variables. In tests conducted over the years, scientists measured the spin or polarization of entangled particles at separate locations. These experiments violated what is known as Bell's inequality, proving that quantum entanglement is real and cannot be explained by classical physics. However, despite its eerie connections, entanglement cannot be used to send messages faster than light. Over the years, entanglement has been demonstrated in many experiments involving particles such as photons, electrons, top quarks, molecules, and even tiny diamonds. Scientists are now exploring how entanglement could be used in revolutionary technologies, such as ultra-secure quantum communication and incredibly powerful quantum computers. The concept of entanglement was discussed even before it was formally named. In the early 1930s, Albert Einstein and Niels Bohr had a series of famous debates about the nature of quantum mechanics. Einstein proposed a thought experiment in which a box emits a photon, arguing that the way the photon is measured determines its behavior, even if it's far away. This was one of the earliest hints at entanglement. In the year 1931, the mathematician Hermann Weyl described how quantum systems with multiple interacting parts exhibit a kind of wholeness greater than just the sum of their parts. 1 year later, Erwin Schrödinger wrote down equations describing entanglement but didn't publish them. By the year 1935, Greta Hermann mathematically analyzed an interaction between an electron and a photon, discovering what would later be known as entanglement. That same year, Einstein, Podolsky, and Rosen formally introduced the EPR paradox, arguing that quantum mechanics was incomplete because it couldn't describe two once-connected systems separately after they were separated. After reading their paper, Erwin Schrödinger wrote a letter to Einstein in German, where he introduced the term Verschränkung, translated as entanglement. He later published a paper where he described entanglement as the characteristic trait of quantum mechanics, the feature that truly set it apart from classical physics. However, like Einstein, he was uncomfortable with it because it seemed to contradict the theory of relativity, which forbids faster-than-light communication. In the year 1946, physicist John Archibald Wheeler suggested studying pairs of gamma-ray photons produced by electron-positron annihilation. 3 years later, in 1949, Chien-Shiung Wu and I. Shaknov conducted an experiment that successfully created entangled particle pairs in the lab, proving that entanglement was not just a theoretical idea, but a real physical phenomenon. Even though Erwin Schrödinger emphasized how important quantum entanglement was, scientists did not publish much research on it for many years after his initial paper. It wasn't until the year 1964 that John S. Bell made a groundbreaking discovery. He introduced what is now called Bell's inequality, which set a limit on how strong connections between particles could be if they followed the usual rules of physics, known as local realism. However, Bell showed that quantum mechanics predicted some situations where these limits would be broken, meaning particles could be mysteriously linked in ways that traditional physics could not explain. Bell's inequality could be tested through experiments, and scientists soon took on the challenge. The first major tests were done in the year 1972 by Stuart Friedman and John Clauser, followed by even more advanced experiments by Alain Aspect in the year 1982. Interestingly, Bell himself discouraged young researchers from following his path, thinking his ideas were too unusual and complex. However, during a talk at Oxford University, a student named Arthur Eckert saw something different. He proposed that breaking Bell's inequality could actually be useful in communication. Eckert then developed a method for securing messages using quantum mechanics, which he published in what became known as the E91 Quantum Key Distribution Protocol. Just a few years later, in the year 1992, scientists took the idea of entanglement even further. They proposed a process called quantum teleportation, which would allow information about a particle to be instantly transferred to another particle, no matter how far apart they were. This astonishing concept was later tested in real experiments in the year 1997, proving that it was not just science fiction. Starting in the mid-1990s, physicist Anton Zeilinger used a technique called parametric down conversion to create entangled particles. This allowed him to develop entanglement swapping, a way of linking particles that had never interacted before. He also helped demonstrate that entangled particles could be used to create highly secure communication systems, laying the foundation for quantum cryptography. These groundbreaking experiments led to global recognition. In the year 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their work with entangled particles. Their research confirmed that Bell's inequality could be violated, further proving that quantum entanglement was a real and fundamental part of nature. To put it simply, just like energy is a key resource for machines to work, entanglement is a resource that enables powerful new ways of communicating and computing. The strange nature of entanglement means that knowing everything about a whole system does not mean you know everything about its individual parts. If two particles are entangled, measuring one will immediately tell you something about the other, even if they are light years apart. However, this is not the same as ordinary correlation found in daily life. Instead, entanglement creates a potential link that can be turned into real correlation through experiments. One of the best ways to understand entanglement is through an example. Imagine a tiny particle breaking apart into two new particles. Because of the laws of physics, these two new particles must follow certain conservation rules. If one has a specific energy, spin, or momentum, the other must adjust so that together they remain balanced. A common case involves a particle with no spin splitting into two smaller particles with spin values that always add up to zero. If one of these smaller particles is measured to have a spin pointing up, the other must have a spin pointing down. This specific case is called a singlet state. At first, this perfect balance might seem like it could be explained by hidden information inside the particles, similar to a prearranged agreement. Bell humorously compared it to a colleague, Boltzmann, who always wore mismatched socks. Even though you couldn't predict the color of one sock in advance, once you saw one, you instantly knew the other must be different. But quantum entanglement is much stranger than that. It only becomes clear when multiple different experiments are compared. Quantum systems can become entangled in many different ways, usually through specific types of interactions. However, this entanglement can also be lost if the particles interact with their environment. This process, called decoherence, happens when an entangled system becomes linked with the outside world, breaking the special connection between the particles. For example, simply measuring an entangled particle can destroy its entanglement with its partner. Mathematically, an entangled system is one where the overall quantum state cannot be broken down into separate parts. Instead of being individual particles, they form a single, inseparable entity. When entanglement is present, you cannot fully describe one particle without considering the other. This idea is central to the famous Einstein-Podolsky-Rosen (EPR) paradox, later expanded upon by physicist David Bohm. In this thought experiment, a source creates pairs of entangled particles and sends them in opposite directions. When a measurement is performed on one, the wave function of the entire pair collapses, instantly determining the state of the other, no matter how far apart they are. The measurement results are random, but always follow the strict anti-correlation rules of quantum mechanics. Imagine you have 2 points in space where measurements are taken. The distance and timing of these measurements can be arranged in such a way that no signal, even one traveling at the speed of light, could possibly connect them. This means that if something were causing one event to affect the other, it would have to move faster than light, which contradicts the principles of special relativity. In fact, according to Einstein's theory, not only is it impossible for any information to pass between these two events, but it is also impossible to determine which measurement happened first. Depending on the observer's point of view, one person might see event 1 happening first, while another person sees event 2 happening first. Since there is no universal agreement on the order of events, one measurement cannot be responsible for causing the other. To resolve this strange paradox, some scientists have suggested that quantum theory might be incomplete. They propose that there could be hidden variables, unknown factors that predetermine the outcomes of quantum measurements before the particles are even observed. If this were true, it would mean that each particle carries with it all the information needed to determine its behavior when measured, eliminating the need for information to travel between them. Albert Einstein and some of his colleagues believed that this explanation was the only logical way to make sense of the paradox. They argued that quantum mechanics, as we currently understand it, must be missing something important. However, experiments have shown that this idea does not hold up when measuring the properties of entangled particles. When scientists measure the spin of entangled particles along different directions, the results do not follow the predictions of hidden variable theories. Instead, they violate a mathematical rule known as Bell's inequality. If the hidden variable theory were correct, Bell's inequality should always hold. But repeated experiments have shown that it does not. This suggests that quantum mechanics really does involve a kind of connection between particles that defies classical explanations. Things become even stranger when these measurements are performed in moving reference frames, situations where, according to the perspective of each observer, their own measurement happens first. Despite this, the results of the measurements remain mysteriously linked, as if the particles know about each other instantly, no matter how far apart they are. This bizarre behavior can be explained by the fundamental differences between quantum mechanics and classical physics. In classical physics, you can measure multiple properties of an object, such as its position and speed, at the same time with perfect accuracy. But in quantum mechanics, certain measurements interfere with each other. For example, measuring a particle's spin in one direction means you cannot precisely measure it in another direction at the same time. This restriction is known as the uncertainty principle. Because of this, the strange connections between entangled particles cannot be explained by hidden variables. Instead, they are an entirely new and non-classical phenomenon. Scientists often refer to this strange effect as quantum non-locality, but this term is somewhat controversial. Some argue that it wrongly implies that information is somehow traveling faster than light, which is not necessarily the case. Instead, what the violation of Bell's inequality actually tells us is that no hidden variable theory based on local realism, meaning one where particles have preset properties and no influence can travel faster than light, can fully explain quantum mechanics. The idea of non-locality is sometimes used in other contexts, such as in quantum field theory, where measurements taken at points in space that are too far apart to influence each other must still obey certain mathematical rules. However, these concepts of local and non-local are not the focus of this discussion. In the field of quantum information, entangled states are seen as a valuable resource. They are difficult to create, but allow for powerful applications such as secure communication and advanced computing. A key concept in this area is known as LOCC, local operations and classical communication. This means that two separate quantum systems, labeled A and B, can perform local quantum operations and exchange classical, non-quantum information. However, this alone is not enough to create entanglement between them. If they are already supplied with entangled particles, though, they can use these resources to perform a wider range of quantum operations. One fascinating application of entanglement is a process called entanglement swapping. This allows two particles to become entangled even if they have never interacted before. The process starts with two separate sources, each emitting a pair of entangled particles. Suppose the first source produces particles A and B, and the second source produces particles C and D. If particles B and C are measured together in a special way, using a Bell state measurement, then the remaining particles, A and D, will instantaneously become entangled, even though they were never directly connected. This phenomenon is a fundamental part of quantum teleportation, which has potential applications in future technologies like quantum networks and ultra-secure communication systems. Quantum entanglement is a fascinating and powerful phenomenon that plays a crucial role in many areas of quantum science. One way entanglement can be used is to allow two separate quantum systems to interact, even when they are far apart. Imagine that a quantum unit, called a qubit, exists in two different locations, one in place A and another in place B. To make them interact, we can first teleport the qubit from A to B. Once it arrives at B, it interacts with the qubit already there. Since both qubits are now in the same location, this interaction follows the rules of a process called LOCC, local operations and classical communication. After the interaction is complete, the qubit is teleported back to its original location at A. However, this process requires two highly entangled qubits, which get used up in the process. This means entanglement is a kind of resource, much like fuel, that enables quantum interactions but gets consumed along the way. Beyond enabling quantum interactions, entanglement is also useful in other areas, such as secure communication and identifying different quantum states. One of the most famous applications of entanglement is quantum teleportation, where information about a qubit is instantly transferred from one location to another without physically moving the particle itself. Another remarkable use is superdense coding, which allows more information to be sent using fewer qubits than classical methods would allow. Many scientists believe that quantum computing would not be possible without entanglement, though some researchers argue otherwise. In quantum cryptography, entanglement is sometimes used in security protocols, but interestingly, it is not always necessary for standard quantum key distribution, QKD, which is a method for securely sharing encryption keys. However, when we want to achieve device-independent security in QKD, meaning we can trust the security of the system without making assumptions about the devices being used, entanglement plays a key role in ensuring this level of protection. One especially intriguing breakthrough involving entanglement happened in August of the year 2014. A Brazilian scientist, Gabriela Barreto Lemos, from the University of Vienna, and her team managed to capture images of objects using light particles called photons that had never actually interacted with the objects. Instead, these photons were entangled with others that did come into contact with the objects, allowing information to be transferred between them. This technique has since been adapted to create infrared images using ordinary cameras, even though such cameras normally cannot detect infrared light. Entanglement is usually created when tiny particles, such as photons, interact in specific ways. One widely used method involves a process called spontaneous parametric down conversion, which generates pairs of entangled photons. Other methods include using a fiber coupler to mix photons, taking advantage of quantum dots that emit entangled light particles, or using the Mandela effect, which occurs when two identical photons meet at a special type of beam splitter. Entanglement can also be formed between a particle and its corresponding antiparticle, such as an electron and its opposite counterpart, a positron, when their quantum wave functions overlap inside a special device called Hardy's interferometer. In the earliest experiments testing a fundamental quantum principle known as Bell's theorem, entangled particles were produced using atomic cascades, a process in which atoms emit entangled photons as they decay from an excited state. A particularly strange and fascinating phenomenon called entanglement swapping allows two quantum systems to become entangled without ever interacting directly. Even when two identical particles are created separately, they can become entangled if their wave functions overlap in space. There is an ongoing debate in physics about how entanglement relates to the nature of time. Quantum mechanics and Einstein's theory of general relativity treat time in completely different ways, leading to what is known as the problem of time. In quantum theory, time is just a background parameter that determines how systems evolve, while in general relativity, time is a dynamic part of the universe, directly connected to the movement of matter and energy. Some physicists, including Don Page and William Wouters, have proposed that the universe may actually be timeless as a whole. However, for observers inside the universe, time appears to exist because of entanglement between different quantum systems. Essentially, the interaction between a system and a clock system within the universe could create the illusion of time passing, even if the universe itself does not truly experience time. This remains an open question, closely linked to efforts to develop a theory that unifies quantum mechanics and gravity. One of the biggest challenges in modern physics is reconciling quantum mechanics with general relativity. Gravity, according to Einstein's theory, is a result of the way matter bends spacetime. However, matter follows the rules of quantum mechanics, and combining these two ideas has proven extremely difficult. In an abstract mathematical model called anti-d space, a concept known as the ADS-CFT correspondence suggests that a quantum gravitational system can be linked to a quantum field theory that does not include gravity. Using this idea, a scientist named Mark van Ramsdonk proposed that spacetime itself might emerge as a result of quantum entanglement. In other words, the fabric of reality as we know it could be built from the entanglement of quantum particles at the very edges of the universe. The study of quantum entanglement continues to reveal surprising and sometimes counterintuitive insights about the nature of reality. From powering the future of quantum computing to challenging our fundamental understanding of time and space, entanglement remains one of the most mysterious and exciting topics in modern physics. The holographic principle is an idea in physics that suggests our entire three-dimensional universe might actually be a projection from a lower-dimensional, two-dimensional surface, just like how a hologram creates the illusion of depth despite being flat. This means everything we see, from towering mountains to distant galaxies, could be a kind of image encoded on a faraway cosmic boundary. This principle comes from string theory and quantum gravity, where scientists propose that the information contained in a region of space is not stored inside it, but rather on its boundary. The idea was first introduced by Gerard 't Hooft and later expanded by Leonard Susskind, who used concepts from 't Hooft and Charles Thorne to refine the theory. Susskind once explained, "The three-dimensional world of stars, planets, and people is like a hologram, a projection of reality that exists on a distant two-dimensional surface." In 1978, Thorne observed that string theory could describe gravity in a way that aligns with this holographic idea. A key example of this principle in action is something called the AD-S-CFT correspondence, a deep connection between quantum physics and gravity. The holographic principle was inspired by research on black holes, particularly an idea called the Bekenstein bound. Normally, you might expect that the maximum amount of information a space can contain would depend on its volume, three-dimensional size, but the Bekenstein bound suggests it actually depends only on its surface area, two-dimensional size. This insight came from studying black holes, where all the information about anything that falls in might be stored on the event horizon, the outer boundary of the black hole. This principle even helps explain the black hole information paradox, a long-standing mystery in physics. However, there are still unresolved issues. Some solutions to Einstein's equations suggest there could be objects called Wheeler's bags of gold that hold more information than a black hole of the same size, which challenges the holographic principle. Beyond black holes, some scientists have suggested that the entire universe could be thought of as being made up of information, rather than just matter and energy. In 2003, physicist Jacob Bekenstein wrote in Scientific American about this idea, which was inspired by physicist John Archibald Wheeler. Wheeler proposed that everything in reality might be fundamentally composed of information, with matter and energy being just secondary effects. Bekenstein wondered if this meant that, as the poet William Blake once wrote, we could see a world in a grain of sand, or if that was just poetic imagination. Bekenstein's work showed a surprising connection between information theory and classical physics. This connection was first noticed in the 1940s, shortly after Claude Shannon, an American mathematician, introduced the idea of Shannon entropy, a way to measure the amount of information in a system. Shannon entropy turned out to have the same mathematical form as thermodynamic entropy, which describes disorder in physics. In thermodynamics, entropy measures how much disorder exists in a physical system. The concept was made precise in 1877 by Ludwig Boltzmann, an Austrian physicist. He explained that entropy represents the number of microscopic ways the particles in a system can be arranged while still looking the same overall. For example, the entropy of air in a room is related to all the ways individual molecules can be spread out and moving, while still maintaining the same temperature and pressure. Shannon, while trying to quantify how much information is in a message, such as a telegraph signal, unexpectedly arrived at a formula that was mathematically identical to Boltzmann's entropy. In his 2003 article, Information in the Holographic Universe, Bekenstein explained that thermodynamic entropy and Shannon entropy are essentially the same thing. In other words, the number of possible physical arrangements counted by Boltzmann's entropy corresponds to the amount of information required to describe those arrangements. The only difference is the units of measurement. Thermodynamic entropy is measured in units of energy per temperature, while Shannon entropy is measured in bits of information. The holographic principle is a fascinating idea in physics that suggests something incredible about the nature of reality. It states that the total amount of disorder or randomness, which scientists call entropy, in any physical system, not just black holes, is not based on its volume, as one might expect. Instead, it is determined by the surface area that surrounds it. In other words, the concept of three-dimensional space might be just an illusion. According to this principle, the entire universe may actually function like a giant hologram, where all the information about what happens inside is somehow written on its outer boundary, much like how a hologram creates the illusion of depth from a flat surface. A key development related to this idea is something known as the anti-de sitter, conformal field theory, AD-S-CFT correspondence, often called Maldacena duality, named after physicist Juan Maldacena. This theory proposes a deep connection between two very different areas of physics. On one side, we have anti-de sitter, AD-S spaces, which are special kinds of curved spaces that appear in advanced theories of gravity, such as string theory and M theory. On the other side, we have conformal field theories, CFTs, which describe the behavior of quantum particles, including those found in models similar to the Yang-Mills theories that explain how fundamental particles interact. This connection has been a huge breakthrough in our understanding of string theory and quantum gravity. It has given scientists a way to describe string theory in a way that doesn't rely on small approximations, making it much more solid. It is also the strongest evidence so far that the holographic principle might actually be true. Beyond just being a theoretical curiosity, this duality has practical applications. It provides physicists with a powerful set of tools to study quantum field theories that are extremely difficult to solve using conventional methods. One of the most useful aspects of this theory is something called strong-weak duality. This means that when the forces in a quantum field theory become very strong and chaotic, making the equations impossible to solve, the corresponding gravitational version of the problem becomes much simpler. This trick has helped scientists better understand a variety of real-world physics problems, including those found in nuclear physics and materials science. The idea of the ADS-CFT correspondence was first proposed by Juan Maldacena in the year 1997. Other scientists, including Stephen Gubzer, Igor Klebanov, Alexander Polyakov, and Edward Witten, helped refine and expand the idea in their own work. By the year 2015, Maldacena's original paper had been cited in over 10,000 research articles, making it the most referenced paper in high-energy physics history. Entropy is a way to measure how random or disordered a system is. Something with high entropy, like a hot cloud of gas, has a lot of randomness in how its tiny particles move. On the other hand, something with zero entropy, like a perfectly known configuration of electric or magnetic fields, has no randomness at all. For a long time, physicists assumed that black holes had zero entropy because they are exact solutions to Einstein's equations of gravity. Since black holes are formed when matter collapses under extreme gravity, scientists believed they were simple and had no internal randomness. But Jacob Bekenstein, a physicist, realized that this idea created a serious problem for one of the most fundamental laws of physics, the second law of thermodynamics. This law states that entropy, the total disorder in the universe, should never decrease. But if a hot cloud of gas, which has a high amount of entropy, falls into a black hole and disappears, then that entropy seems to vanish from the universe, breaking the law. To fix this problem, Bekenstein proposed a bold idea. Black holes must actually have entropy, and it must increase whenever they absorb something with entropy. He argued that for any given amount of space, the black hole that fills that space must have the highest possible entropy. Otherwise, if some other object had more entropy than a black hole of the same size, then feeding it more matter would create a black hole with less entropy than before, which would once again break the laws of physics. Bekenstein also calculated that the entropy of a black hole is directly proportional to the area of its event horizon, the invisible boundary around it where nothing can escape. This was a revolutionary idea, because it suggested that information about everything that has ever fallen into a black hole is somehow encoded on the surface of the black hole, not inside it. A strange consequence of this theory comes from something called gravitational time dilation, which happens near the event horizon of a black hole. From the perspective of a faraway observer, time seems to slow down as an object gets closer to the event horizon. In fact, at the horizon itself, time appears to stop completely. This means that, in a sense, any object that falls toward a black hole never truly crosses the event horizon from an outside observer's point of view. It just gets closer and closer, frozen in time. Since quantum physics requires time to flow in order for information to change, this means that all the information about the falling object never actually disappears. Instead, it remains imprinted on the event horizon. This is what led Bekenstein to conclude that black hole entropy, and possibly all entropy, is tied to surface area, not volume, reinforcing the idea that the universe itself might be a kind of hologram. A long time ago, the brilliant physicist Stephen Hawking made a surprising discovery about black holes. He found that the total surface area of the event horizons of black holes, essentially the invisible boundaries around them, always gets bigger over time. The event horizon is a special kind of boundary where even light cannot escape once it crosses over. It is defined by geodesics, which are paths that light follows in curved space. If two of these paths start moving toward each other, they will eventually collide, and from that point forward, they will exist only inside the black hole. However, in most cases, these geodesics spread apart, which means that the surface area of the black hole's horizon keeps expanding. This groundbreaking discovery became known as the second law of black hole thermodynamics, which was similar to the second law of thermodynamics in regular physics, where entropy, a measure of disorder, always increases. At first, Hawking was skeptical about this connection. He reasoned that black holes must have a temperature of absolute zero because they do not emit any heat or radiation. If they had no temperature, then they could not behave like a thermal system in equilibrium with their surroundings. But later, he made an astonishing breakthrough. Black holes do, in fact, radiate energy. This realization changed everything. If black holes radiate energy, then they must also have a temperature. That means they must follow the same basic rules as any object in thermal equilibrium. Black holes should not only absorb particles, like light, photons, but also emit them in just the right amount to maintain balance. In physics, a system that does not change over time, called a time-independent system, usually does not give off radiation. Hawking initially tried to prove that black holes followed this rule and did not emit anything. But after a deeper analysis, he was shocked to find the exact opposite. His calculations showed that black holes do radiate, and they do so in a way that allows them to reach equilibrium with their surroundings. Through his mathematical work, Hawking discovered that the entropy, or disorder, of a black hole is linked directly to the area of its event horizon. More specifically, he found that a black hole's entropy is equal to 1/4 of its horizon's surface area when measured in Planck units, a fundamental scale in physics. Entropy is a measure of how many different ways a system can be arranged microscopically while still looking the same on a larger scale. Normally, we expect entropy to depend on volume, the amount of space inside an object. But black holes are different. Their entropy is based on surface area, not volume, which is a huge mystery. Later, a physicist named Raphael Bousso expanded on this idea and proposed a new way to describe this entropy bound using something called null sheets, which are special surfaces in space-time. Hawking's findings also raised another puzzling question. Where does the radiation that black holes emit actually come from? His calculations suggested that the light escaping from a black hole is not directly related to the material that the black hole swallowed earlier. Instead, these escaping photons originate right at the edge of the event horizon and stay there for a long time before finally escaping into space. Meanwhile, any matter falling into the black hole crosses the horizon much later. Since the incoming and outgoing energy only interact at the moment they pass each other, it seemed unlikely that the outgoing radiation could somehow remember what had fallen in. Hawking interpreted this to mean that when black holes absorb photons that exist in a pure quantum state, they re-emit new photons in a different way, one that follows the rules of a thermal mixed state. This was deeply troubling because, in quantum mechanics, pure states are not supposed to turn into mixed states. This went against the fundamental principles of quantum theory and suggested that quantum mechanics might need to be changed in some way. Concerned by this paradox, another physicist, Gerard 't Hooft, studied Hawking radiation more closely. He realized that when black holes emit radiation, there is actually a way for incoming particles to influence the outgoing ones. As a particle falls into a black hole, its gravitational field slightly changes the shape of the event horizon, which could, in turn, affect the radiation that gets emitted. In essence, the horizon of the black hole records information about the falling particles. Tuft found that these deformations on the horizon resembled something familiar from string theory, the mathematical framework that attempts to describe the fundamental nature of reality. He suspected that string theory might hold the key to solving the mystery of black holes. Building on this idea, physicist Leonard Susskind made a major breakthrough. He had been developing the concept of holography, the idea that everything happening in a volume of space can be fully described by information stored on its boundary. Susskind argued that the tiny fluctuations on the surface of a black hole contain all the information about both the particles falling in and the radiation coming out. This meant that the surface of the black hole essentially acts like a hologram that encodes everything that happens inside. Susskind showed that highly excited strings, long, stretched-out versions of fundamental particles, could be directly linked to black holes. This was a huge revelation because it connected the mysterious nature of black holes to the well-established principles of string theory. Ultimately, this work suggested that the so-called black hole information paradox could be solved if we think of quantum gravity in an entirely new way. Instead of treating space and time as fundamental, this theory suggests that space-time itself is just an emergent property that arises from the interactions of a lower dimensional system, the surface of a black hole. Back in the year 1995, physicist Leonard Susskind, along with his colleagues Tom Banks, Willy Fischler, and Stephen Schenker, introduced a groundbreaking idea that helped shape our understanding of the mysterious M-theory. They proposed a new way of looking at it using something called a holographic description. This concept involved tiny but incredibly powerful black holes known as D0 brains, which are key elements in type II string theory. The foundation for this idea had actually been suggested earlier by three other physicists, Bernard de Wit, Jens Hoppe, and Hermann Nicolai. They originally described it as a way to understand two-dimensional brains in an 11-dimensional version of gravity called supergravity. Later on, they realized that the same mathematical models could be used to describe the behavior of tiny black holes under specific conditions. By using the principle of holography, Susskind and his team were able to argue that these black holes provided a complete, non-approximate version of M-theory. Then, in the year 1997, physicist Juan Maldacena took this idea even further. He introduced the first holographic description of a larger, more complex structure, an object in a four-dimensional space known as the type IIB membrane. His work finally solved a long-standing puzzle: how to use string theory to describe a gauge theory, which is a crucial part of quantum physics. This was a major breakthrough because it showed how string theory is connected to certain types of quantum field theories, which govern the behavior of fundamental particles. Now, let's talk about information. In physics, the amount of information in a system is measured by something called information entropy. This is calculated using a mathematical concept, the logarithm of the inverse probability that a system is in a particular state. Put simply, it tells us how much randomness or disorder exists in a system. Interestingly, this definition of entropy matches the well-known Gibbs entropy, which has been used in classical physics for over a century. When we apply this idea to the physical world, we reach a surprising conclusion. For any given amount of energy inside a certain volume of space, there is a maximum amount of information that can exist within that space. This is known as the Bekenstein bound. If the information exceeds this limit, the system becomes so dense that it collapses into a black hole. This leads to another fascinating insight. Matter itself cannot be divided infinitely into smaller and smaller pieces. There must be a fundamental level where the subdivision stops. If we could keep breaking down particles endlessly, the amount of information contained in even a single particle would become infinite, violating the laws of physics. The holographic principle suggests that nature has a built-in limit to how small things can get. The most precise and well-established version of this idea is something called the ADS-CFT correspondence, developed by Juan Maldacena. But years before that, in 1986, physicists J. David Brown and Mark Henno had already laid some of the groundwork. They proved that in a special kind of three-dimensional gravity, the system follows mathematical rules known as the Virasoro algebra. This discovery showed that the underlying quantum theory must be a two-dimensional conformal field theory, a key part of modern physics.